Hey everyone, how are you doing? You all ready? Any questions over homework or anything else at this point?
The number 24 for the 1.4, please.
Number 24?
Yes, sir.
Okay. So make sure I have this right. Limit t approaches 0 in parentheses. Does this look right?
Yes, sir.
1 over t minus 1 over t squared plus 1. Okay, so for this one, this is a limit. We're trying to evaluate the limit algebraically. So the first thing we want to do is try direct substitution, right? We're going to take t, we're going to let it go to 0 and see what happens. And you can see right here, as soon as you try and plug 0 in here, this is undefined, right? You have division by 0. If we plug 0 into this, we do not have division by 0. We have 1 over 1, right? If we plug in 0 for t. So this is not a problem, but this is, right? So the question remains, how do we go about figuring out what this limit is, right? So anytime we have 0 on the bottom like this, 1 over, here we have 1 over 0, right? This is an issue, right? 1 over 0 is an issue because it is undefined, right? Now it is not the form 0 over 0, which is something we had before, right? This is the situation where we have something bad happening, right? This is bad. So we'd want to do some algebra or some sort of trick. We have not seen this yet. Okay, we've not seen this scenario yet. And on your limit summary, remember I told you on your formulas, you have that limit summary sheet.
I forgot about that.
Yeah, this is on here. Okay, this is on here. However, let's see what happens if we try and do algebra. Let's just try and do some algebra and see if it gets us anywhere. So the most I could probably do is combine both these fractions together into one fraction. That means get a common denominator. So let me try that and just see what happens. Limit t goes to 0. Okay, so what I'm going to need to do is I'm going to need to take my first fraction, give myself some space here, and I want to multiply it by the denominator on the other fraction, t squared plus 1 over t squared plus 1. And then I'm going to subtract from that 1 over t squared plus 1. Now this fraction, I need to multiply that by the other one's denominator, which is t over t. All I'm trying to do is combine these two into one fraction, see if things get any better or not. So when we now do this, my new numerator, I multiply here, t squared plus 1 times 1 is t squared plus 1. Then I will subtract from that what I get when I do 1 times t, which is t. And then all of that divided by t squared plus 1 times t, the denominator, right? Okay, now did this get us anywhere? Let's see. If we let t go to 0 right now, let's see if anything better happens. So if t goes to 0, the top goes, let's see, 0 plus 1 minus 0, that should give us a 1 on top. And on the bottom, we get 0 plus 1 is 1, but then times 0, so we get 0 on the bottom. So again, we're kind of in this form that we have not really looked at yet, right? What's going on here? The algebra that we've done to try and make things nicer hasn't really helped us to get anything to cancel out. You all see that? Like in the previous problems and the problems we did last class, most of the other homework problems, something eventually canceled out. Nothing is canceling here. So this is a good question to actually start class with, because we actually do need to figure out what happens in this case. So let me bring up our formula sheet. Let me see, I'm going to go to our Canvas page real quick. And under files, the limit summary. Okay, I'm going to download this and then open it up. Actually, I think I'll put it right here in the formulas. I'll make a new one. Limit summary. Just going to insert it in here.
Is that Mathematica program you were telling us about last time?
What I'm using right now
Yes.
is just OneNote.
Okay.
Yeah, this is just OneNote. Okay,
Never
here we
seen
go.
that before.
All right, so here we go. This is the summary of what happens when we see certain types of limits. And in the problem that we have right now, what we are seeing is 1 over 0, right? That's what we're seeing, 1 over 0. So what we want to see here is that the numerator is a fixed non-zero number. Do you agree that 1, right, is a fixed, meaning it's not changing, it's not, you know, like a variable, so it's fixed and it's not 0. Anytime we have that divided by 0, we are going to be looking at where is it, these cases over here. Okay, these cases over here. And when you look at this, I know this looks complicated, but let me just kind of illustrate what this means. Let's look at the first one. When it says fixed with the little plus up here, that means that your numerator is a positive fixed number. All right, here, this one would mean that your numerator is a negative fixed number. Here, the numerator is a positive fixed number. Here, the numerator is a negative fixed number. So that's what that little plus and minus means. So in our case, we have a positive fixed number, right? Positive fixed number. And the denominator is headed to 0. So basically, looking at this table, we have, it can't be this and it can't be this, because those are both negative fixed numbers, right, on top. So our answer is either going to be infinity or negative infinity. It will depend on what's happening to the denominator. It depends on whether or not we're approaching 0 and approaching what this little negative means from the left and then from the right. So are we approaching from the left or from the right here? Let me go back and grab that problem. So which side of 0 are we approaching from?
We're approaching from both.
From both, good. Because it doesn't say, right?
Mm-hmm.
Doesn't say. So if we think about this, that means we have to check both sides. And according to this table, if our numerator is fixed and positive, then if we approach 0 from the right side, our answer is positive infinity. If we approach 0 from the left side, our answer is negative infinity, which means that the graph is doing something like this. Like from one side, it's going down and the other side, it's going up. So what can you tell me about the limit then? From both sides, the original. What's that?
It doesn't exist.
Doesn't exist.
So there's no limit.
Yeah, because we said last class that in order for a limit to exist, you have to be going from both sides headed to the same place, which is not happening here. One side's going down, one side's going up. So I will admit, we're getting a little bit ahead of ourselves. The book, okay, the book is weird because in the book, in this section right here, 1.3, when they tell you that when you get fixed over 0, okay, in 1.3, the book tells you at this point to say does not exist. Okay, but we're going to find out a little bit later that sometimes it does exist. You have to inspect it from both sides. So I would not ask you anything like this yet on a test because we're going to get into more depth into this later. So if you're a little confused as to what's going on here, and I hadn't shown you this table yet for these, we've been working just on that right there, 0 to 0. Then just stay tuned. It'll become clearer as we move further through this section.
Just for clarification, by fixed, it's just like it's a constant number. There's no like x minus 1 or whatever. It doesn't have
That's
a
right.
0 factor. Okay.
That's right. It's just a constant. Could be 4, could be 10. Okay, were there any other questions? So last class was all about, and I will say thank you for having your cameras on. This is good. I like this. Almost everybody has a camera on. So last class, we did a couple of things. We started out by saying, let's talk about this idea of a limit, and we did everything visually, right? Everything was graphs and coming from the left and right. And then after that, we switched gears and we said, okay, now instead I'm going to give you a limit algebraically, okay, which means I write down the limit like this problem here. And then I ask you what's happening. And you try and figure it out without the graph. And for that, we had this situation 0 to 0, which was bad. And in that scenario, you have to do some algebra, some sort of trick. And we saw like, factoring, conjugates, complex fractions where you get common, put fractions together. And in your homework, there should have been a lot of practice with that. We're not done with this section. We still have a few more things to do. But before I can do it, I have to give you 2 very special limits. Okay, so there are 2 limits that everyone here needs to know. Here they are. And at this point in time, I cannot show you why they are what they are. Okay, so there's nothing I can do to explain to you why these are the way they are. So let's just look at this right here. Sine of x over x, limit as x goes to 0. Let's just look at that. Let's start by looking at the graph. I'm going to go graph this as a function, sine of x over x. Okay, so I'm going to go bring up Desmos, and I'm going to do sine x over x. And that is the graph of sine of x over x. Now, is it clear to everybody that you cannot plug 0 into this function? That if you try and plug in 0, sine of 0 on top gives you 0, and then 0 on the bottom gives you 0. So you have a division, you have 0 over 0, which is bad. But if you look at the graph, it looks like from the left, right, here's 0 on the x-axis. If we look up here from the left and from the right, what does it look like we're approaching?
1.
1, right? So the limit should be equal to 1, and that's what I'm telling you need to know, is that this limit as x approaches 0 of sine of x over x will always be 1. Also, you can flip it over. You can have it the other way around. If the x is on top and sine x is on the bottom, you will get the same answer. So let me graph that one for you. So that's the green one. Okay, so can you all see what the green one? Same thing happens there?
Yeah.
Okay. So when I've told you that if you get 0 over 0, you want to try some algebra. But what I'm saying to you is that if you get that limit x approaches 0, sine x over x, we know that that gives you 0 over 0. We know that's bad, and we know that we need some algebra. I'm telling you right now that there is no algebra that you can do. Like there's nothing you'll be able to do to show me that that's equal to 1. So we just have to rely on the graph right now. And everyone here needs to take it on faith that that's the answer. Later in this class, we'll be able to prove that it is 1 without the picture, but you have to wait till later. Okay, so just take it on faith, all right? Now, The other limit that you need to know, the other one, is the limit as x approaches 0 of cosine of x minus 1 over x is equal to 0. So if we were to just try this real quick and just try and plug 0 in for x, cosine of 0 would be what? So I'm trying to figure out what is this turning into? So cosine of 0 is
1.
1 minus 1 over, and then if x is going to 0, then that's going to be 0, and that's 0 to 0, and that's bad, right? And we need some algebra. But I'm telling you again that there's no algebra you're going to be able to do to convince yourself or convince me that the answer is 0, right? So you're just going to have to take that on faith.
Is it just because it's just knowing trig function values from the unit circle instead of actual algebra, or?
There's just, I mean, well, we know that with trigonometric expressions from pre-cal, there's all
Mhm.
sorts of things you can do to trig expressions to, where you can bring in identities and do all these different things. What I'm saying is that there's no identity or nothing from pre-cal that we're going to be able to do that's ever going to turn that into something where we cancel out things and get, oh, the answer is 1, or, oh, the answer is 0. There's just nothing. Now, there is a way to do it, okay? There is a way to prove it. Without what we need, later on when I prove it, it's just going to be like, oh my gosh, that's so easy. But before we do that, if you wanted to see see it, I could show it to you, but you'd have to come to my office hours. It'd probably take us about 45 minutes. I could do it. I could show it to you, but it's just something you would never think to do. It's actually a really cool proof, but it's just not something that you would naturally think of. All right.
I'm going to leave it up to your discretion, sir, when you think I'm
Yeah.
ready.
Yeah. Okay. So is it okay? I'm gonna kind of like say everyone here needs to know these, right? Now, of the two, the first one is the most important one. This one right here. That's the most important one. This one is not used as much, but this one comes up quite a bit. And because it comes up quite a bit, I want us to look at that in a little more depth, because I'm going to present it to you in a slightly different way than it shows here. All right, so let me start this over. Here's what you've been told. You've been told that the limit as x approaches 0 of sine of x over x equals 1. I told you to know that, remember it, there. But really what I want you to know is this. If you're ever taking a limit, okay, I don't care what the limit is, it doesn't matter what variables here, and it really even doesn't matter what it's approaching, okay? Who cares? X could be going to 2, X could be going to 5, T could be going to -3. It doesn't matter what the limit is, okay? It doesn't matter. If you have up top sine, and inside the sign, you have some expression. I don't know what it is. I'm just going to call it junk, okay? Because it's just some junk sitting in there, okay? Whatever it is. Could be just x, could be x squared plus 1, could be tangent of x. It doesn't matter. It's just some junk sitting inside of there. And then that whole expression is divided by that same junk, okay? Now, the key here is that this junk here and this junk here, they have to be the exact same junk. So like, look up here. Here, that's x and that's x, right? You see that junk matches, right? These match exactly. So if you're taking a limit, doesn't matter what it is, and you've got sine of something over that exact same thing, your answer will be 0. I mean, sorry, your answer will be 1 if, okay, if the junk is heading to 0. So what do I mean by this? This is the thing you need to know, okay? So what do I mean by this? Let me give you an example. Limit x approaches 3 of sine of x minus 3 over x minus 3. The answer to that is 1. Now, why is it 1? Well, I have something in here, right? X minus 3. And that matches exactly what's down here. And when I take this limit, right, when I let x go to 3, that junk goes to 0 and that junk goes to 0. So as long as both of the junks go to 0, then this limit's going to be 1. I'll give you another example. limit x approaches 0, sine of 5x over x. All right, be careful here. Is this 1?
No.
No.
Oh, because the junk's not the same.
Junk's not the same. Do y'all see that? The junk you have in here is not equal to the junk you have down here. You have a 5x inside the sign and you have an x down there. So maybe you're thinking to yourself, well, wait a minute, can I just pull the 5 out of the sign?
Yeah.
Can you just pull a 5 out of a sign? Is that the way numbers work with trig functions? Can you just pull constants out? No, you cannot. All right. In
Has to
fact,
be-
I'll remind you of something that you had in pre-cal. Remember when you had sine of 2x? This is not 2 sine of x. Like you can't just pull the 2 out. If you go back to pre-cal, you'll see this actually turns into 2 sine x cosine x. That was called the double angle formula.
Question, wasn't it,
Yes.
there was something with the trig you could pull to the front, but I think it was like an exponent or something like that. You could move to the front, but not with inside the argument.
The only time you can pull exponents out the front is if it had a natural log in it or a logarithm. That was a property
right.
of logs.
Yeah, that's right.
Yeah. So we cannot pull this 5 out, can we? Right? We can't pull this 5 out. However, this is kind of the cool, tricky part. Would this answer be 1? Would it be 1 if that was 5x on the bottom? Would it be?
Yes.
Okay. Can you make that a 5x?
I mean, I feel like you can, but then you're messing with well, I mean, if you put a 5 in front of the sign in the beginning, yeah.
Yeah. What if we just multiply this whole thing by 5 over 5? What if we do that? What would we get? Let's see. We would have limit x goes to 0. Now, this times this, right? All I would really do is just put the 5 in front of the sine x. I cannot move that 5 inside, right? For the same reason I can't pull the 5 that's inside out, you can't just push a number into a trig function. So that 5 just sits out in front, but now my bottom is 5x, right? And if we focus our attention on this, that is exactly limit of who cares of sine of junk over junk. That part right there should go to 1, shouldn't it? And then I just have a 5 next to it. So this becomes 5 times 1, which is 5. Does that make sense? That's tricky, huh? Come in here with a 5 and just put a 5 over 5. Remember, 5 over 5 is a 1, right? So that doesn't change the problem. So I'm gonna now give you some other problems, and you're gonna see things are gonna start to get a little weird here. You ready? How about this limit? Oh, you know what? Let me give you one more before we do something weird. Okay, for this one, can we use the formula here? Can we use this?
No, not right now.
Not yet. The junk doesn't match. Now, also, aren't they flipped over? Aren't they opposite?
The
Right,
opposite doesn't matter. It's the same
That's
thing.
right. It doesn't matter for this special sign thing that we're looking at. So the fact that it's flipped over, we should still get 1, but these two things, these two junk things have to match. So how can I make a match? It's almost so
Divide by
easy
3.
that it's hard.
So it's like multiply by
Well-
1 over 3,
So if we multiply by 1 over 3, we have to do it on the top and bottom,
right?
right? We'd have to do it on top and bottom. So we could do that. We can divide both top and bottom by 3, but how about this though? I mean, why not just pull the 3 out in front and rewrite it? Just rewrite it. I mean, isn't 3 times x really mean 3 times this fraction?
Yep.
And that's
So
all it is really algebraically. And so here, that right there goes to 1. So what would your answer be?
3.
3. Does everyone understand that? That's different than the last problem. Last problem, we didn't have that because in the last problem, we had a 5x inside the trig function. We couldn't pull the 5 out. So we had to magically make a 5 appear down here. So we had to multiply top and bottom by 5. Here, we had an x in here. So we want that to be an x. So we don't want the 3, but all we have to do is just use basic algebra properties that the 3 is really like a 3 in front. Okay, with that, I think we're ready for something more difficult. So how about this? Limit x approaches 0 of tangent of x. Hold on, let me start this over. Limit x approaches 0 of tangent of, I'm going to do 3x, not x, over sine of 5x. Now, in all of my years teaching Cal 1, every time I get to this type of problem, students start like freaking out when they realize what needs to be done to do this, because it's so unnatural what we're about to do. Like it's not like follow step A, B, C, D. You really have to think about what you're trying to accomplish. All right. So what's that?
I was going to take a guess, maybe.
Okay.
Are we going to have to basically turn the tangent back into identity like sine over cosine and then try to reduce the signs out with like cross multiplication? So then multiply the top by 1 over sine, and then you get 1 over cosine of whatever.
We may have to, yeah, we may have to turn the tangent into sine and cosine. We may do that. Exactly. So you want to be thinking that. But with any limit, the first step is to always just check to see what's happening. Okay. So I would like us right now to figure out what happens if we let x go to 0. So if we let x go to 0, 3 times 0 is 0, right? So the top is going to be headed towards tangent of 0. And the bottom is headed towards sine of 0. And from pre-cal, everyone in here should know, because you passed pre-cal, that tangent of 0 is 0 and sine of 0 is 0. So what you're getting here is something bad. And we have to do some sort of algebra then, or some sort of trick. Okay? Y'all with me?
Yes, sir.
So now the way that I look at this is I always say to myself, what is causing the problem? Like, what is making this limit not be some answer? And that would be the fact that I have division by 0, right? That automatically kills everything, right? So the part that's causing the division by 0 is the sine. And so this right here, this sine of 5x is the problem, right? That's what's creating the issue. So I'd really like to try and make that sine of 5x not cause the problem. I want to try and manipulate this somehow so that the sine x is no longer creating this division by 0. So the first thing I'm going to do is I'm going to split this up. This is just algebra. I mean, that's what this expression is, this, right? I mean, all I'm doing is sliding the tangent away from the sine of 3x, or sine of 5x that's on the bottom. Okay, so I've pulled that apart. You with me?
Yes, sir.
Now, what would you love to see up here? What would it be really nice to have up there?
A 5x.
A 5x, right? Wouldn't it be great if we had a 5x up there? Because if we had a 5x up here, it would then make this thing turn into a 1 when we take the limit. But there is no 5x up there. So I'm going to make a 5x appear. Ready? Here it comes. I'm going to do it in a different color because I'm going to bring this in. I'm going to now multiply this by 5x over 5x, because that's just a 1. And then I'm going to slide the 5x on top here. All right, so now let me write the new line. This limit is now tangent of 5x times 5x over sine of 5x times what's still over here?
Wait, is that tangent supposed to be a 3x?
It's a 3x, sorry, thank you.
Yep,
What's still over here?
1 over 5x.
1 over 5x, right? Okay, so let's see what we accomplished. All right, remember the problem was the division by 0 that was being created by the sine, which was being created by the sine of 5x. So I peeled it away. I said, let me fix this, okay, by making a 5x appear on top. So now if we take the limit again, we know that that goes to 0. Tangent of 0, 0. We know this goes to what? 1,
1.
right?
1, yep.
And that's good. I mean, 0 times 1 right now, 0 times 1 is just 0. We don't have division by 0. But what? I mean, look, this is crap now, right? That's undefined. So one way you could look at it is like, we fixed one problem, but to fix it, we created a new one. Y'all see that?
Mm-hmm.
So then you might be saying to yourself, well, this is just a bunch of crap because, you know, I still can't do it until you realize this. All right. This is the part that people are like, okay, I don't know about that. That's crazy. All right. So I'm going to rewrite the tangent as sine of 3x over cosine of 3x, because that's the definition of tangent. Okay. And I'm going to highlight in blue what the problem is. The problem is that 5x is causing division by 0 again, isn't it? Does anybody see what I'm going to do? Anyone see what I'm about to do?
Cross out some of the sine x's.
But to cancel the 5x's out, so 5x would just be 1 over sine or the 3x sines.
These signs can't cancel each other because they have different arguments, right? 3x and 5x, so we can't cancel those. Let me write one more step. Usually when I write the next step, someone will see it. Okay, so all I did here was rewrote sine of 3x over cosine of 3x as sine of 3x over 1 times 1 over cosine of 3x. I just split those apart. You all see that? Just algebra. Okay, highlighting again, this is the part that's causing the problem. I wish this wasn't a problem. Somebody see what I'm going to do? I will ask you to focus your attention on this right here. Let's see it.
Just 1 over 1.
We should put the 5x under the sine.
Okay, you're almost there, Cody.
So would you
said
like
put the
do
5x under the sign?
like
What's that?
3 and 5? Like you would kind of make it into like 15x to combine
Yeah.
them?
Okay, so Cody said we could put the 5x under this, and then it almost looks like junk, like sine of junk over junk, doesn't it?
Mhm.
Almost, but they're not the same because it's 3x and 5x. So why don't we do this instead? Why don't we take just the x and slide it under here? Okay, just the x. Now, am I allowed to do that? Remember, everything on the bottom is being multiplied, right? This is all multiplication. Multiplication of fractions means you can change the order in which things are done. So sliding things around is perfectly legal. I'm going to slide just the x. And what else do I wish was there?
You wish you had a 3x.
I wish I had a 3 there with the x, right? So over here on the side in green, I'm going to make the 3 appear. 3 over 3. Yes? And I'm going to grab just the 3 and slide it out over here. So I'm going to move the x and a 3 over there and rewrite the entire expression and see what I get. I now have sine of 3x over 3x. I have 1 over cosine of 3x. I have 5x over sine of 5x. And I have, what do I have here? Because I slid things around. So what's still right here?
Yeah, 1/5
Just 1 over 5.
times
then
3 over 1.
3 over 1. Now, any questions on that?
I'm just curious, but why 1/5x is still the problem when it's like the other things are still gonna give us zeros as well?
Well,
Or
you can
multiply
have
out.
0. You just can't have division by 0.
Well, no, but it's just the, like the sine of 5x is still gonna be 0, so I don't know why the 5x over there is the only problem, like when we break this up
Right?
further.
This is going to be 0. The
Or no,
sine-
never mind, that's 1, never mind,
yeah,
okay.
yeah, because it's with that, that turns into a 1. Yeah.
And then the sine, okay, I got it, never mind.
So I'm moving this. So even though this was the problem, the key to this is understanding that really this part in blue here is a problem we cannot get rid of. But because we got lucky and there was a sign in the numerator, we were able to exploit that formula by moving that x over here and then introducing a 3. And now look at all these pieces. Every one of these, something nice happens. So this now, when we take the limit, goes to 1 because it's sine of junk over junk. This, okay, what is cosine of 0?
1.
1. 1 over 1 is 1. Okay, times. Now this, well, that's where we started the problem, right? That's going to be a 1 also. But now notice we don't have any more variables, right? It's just numbers. So this is 1/5 times 3 over 1. So our answer is just going to be 3/5. All right, look, we could spend an hour doing problems like this, really. I mean, we could, but you have these in your homework and you have the homework solution videos to help you get through these. So I'm going to leave you with that one example and then just kind of throw you to the homework and hope that you can figure it out. Okay. Yeah, let's do that. All right, so here are some problems that I normally would do. You know what? Y'all want to do one more? Y'all want to do one more? We can.
Yeah, 1 more would be good.
One more? Okay. This one down here is like kind of what I just did. That problem right there is very similar to what I just did. How about you try to do this one right here? This one I think is not as hard as the one we just did, but I'm going to put it up here and let me give you, I don't know, do about 5-6 minutes to see what you can do. I'll put a timer up here. Hold on. I'll put that back up. Don't worry. Six minutes might be a little bit too much, but all right. And I think I'll bring another one up here. Another 2, just in case someone finishes those and wants to practice something else. There we go. Okay, see what you can do with those in the next 6 minutes. I think that's probably enough time. All right, so Gabriella, did you get anywhere with this?
Yes, sir. I was almost done with I guess the first one, tan 5x over 5. I mean, tan 5x over x. What I did was I broke down the tan and moved the x from the bottom. So I got sine 5x over cosine 5x times 1 over x
Okay,
to break it up. And then I broke the sine and cosine to where we got sine of 5x over 1 times 1 over cosine 5x times 1 over x.
good.
So
Does
that's,
everyone follow that? That's perfect so far. Real good with
thank
that?
you.
Okay, good.
So
Now,
what I did from there was I multiplied a 5 over 5. And so then I carried the bottom x and the bottom 5 from those two fractions, and I carried them across to the sine 5x over 1 to where I got sine 5x over 5x times 1 over cosine 5x times 5 over 1. And then that was just a matter of solving that, and yeah, that's where I
yeah,
left off.
perfect. So let's see, where do these go? This goes to 1, that goes to 1, that goes to 5, right? So your answer is 5. Good. Anybody get the part D?
I think I might have got it. So,
Okay,
Yep.
So I separated it out. So I took the first x off and I
okay,
did x over 1, and then cotangent's just like a flipped tangent. So
okay.
it was cosine x over sine x.
Mhm.
And then I split that up further. So it would be x over 1 times 1 over sine x, and then cosine over x, or cosine x over 1. And then I combined the first two, which gives us the rule, which is 1, and then cosine x over 1, which is also 1, I believe.
Yes, good, perfect.
So the answer just ends up being 1.
1, there you go. Good, good, good. Anyone have a question on that one? Okay, this is good. Okay, how about the last one? Anyone get to that one?
Yeah, isn't it just 1 because the junk's the same?
We have something that's different. We have that squared there. That makes a difference because this formula only works if it's sine, not sine squared.
Oh, okay.
Well, you can use the trig identity, right?
You could, yeah. And what would it turn into?
I think it would be cosine plus 1. Or no, 1 minus cosine.
1 minus cosine
Squared.
squared. We could turn that into 1 minus cosine squared of t. We could. Does that help us though?
No.
I mean, it may be that you can try and get there that way, but let me suggest something here, unless someone else has it. That's what we have, right? It's the same thing. But what does sine squared mean? That just means sine t times sine t, right? Isn't that what it means? Times 1 over t. That's what sine squared means. And then I can just look at those as being over 1. And then I can just combine those two together. So I'd have limit t goes to 0, sine t over 1 times sine t over t. And this one is the one that is the junk over junk, right? Sine and junk over junk. And that goes to 1. And so we should be okay here. Let's see, where does that go? Sine of 0 is 0, right?
Yep.
0 divided by 1 is 0. See, there's no division by 0 there. It's just 0. And then times this goes to 1. So your answer is 0. Okay, I hope that that all makes sense. Again, you'll have problems in your homework where you have an opportunity to practice a little bit more on this.
I have just a quick question for the tan 5x over x. So I just did it like a weirdly simple, I don't know if this is right. I just times it by 5 over 5 like you did before, and I got 5. Would that still be like a correct way to do it?
You use it like a 5 over 5 here and then put the 5 under here. So that 5
Yeah,
here.
and then
And you said that this turns into 1?
no, I got 5 tan 5x over 5x, and you said that 5 times, because tan 5x over 5x would be 1, so it'd be 5 times 1 equals 5.
Why is tangent of 5x over 5x going to go to 1?
Because it has the same, is it because it's not in,
It's because it's not sine. It has to be sine.
oh, okay, gotcha.
Yeah, okay, so I see what you, so look, if I did this limit, watch, limit x goes to 0. Let's say we did cosine of 2x over 2x. That is not 1.
Okay.
It has to be a sine for this to work.
Gotcha, okay. Okay,
Okay, we need to proceed. We need to move on. Okay, so we are moving on to, let's see. So that's 1.4, right? So the next section, you know, in order would be 1.5, all right? Now, what I like to do is I like to do 1.6 before 1.5, all right? I like to do it that order. And I'm going to do that this way because we'll be able to cover both of these today. I'm going to do 1.6 before we do 1.5. And if you follow our schedule, that shouldn't make a difference because the homework for 1.5, today we're supposed to cover 1.6. So we will get through hopefully both of these in the next couple of hours here, okay? 2.5 hours. Do y'all want to break 5 minutes or you want to just plug away? I don't care.
Take a break a little later is good with me. I don't know about everybody else though.
Look, I tell you what, 1.6 it has 2 sections to it. So why don't we do the first section of 1.6, then we'll take a break and we'll come back and do the second section. Let's do that. Okay. All right. So 1.6. So now what we're going to do is we're going to be dealing with limits that involve infinity. So remember, infinity is not a number, right? Infinity is an idea. So you can never say, oh, x equals infinity. That makes no sense, all right? So we'll start off there. Like I said, this section is broken into 2 different ideas. The first idea are what are called infinite limits. And that means that when we take the limit of something, our answer is going to be infinity or negative infinity. And we have seen this already, okay? Here's an example of a function in a limit that would give you an answer of infinity. I'll write it down here on the side. If we take the function f of x equals 1 over x squared, and I ask you, what's the limit as x approaches 0 of that function, right? Then if we could look at the graph of this function, we could see that this is the graph. We can see that as we approach 0 on the x-axis, as we come in from the left, the function heads to infinity. As we come into from the right, the function heads to infinity. So from both sides, the function becomes infinitely big. And so our answer is infinity. So this idea of infinite limits that we're talking about is a limit where your answer is infinity or negative infinity. But that's what an infinite limit is.
And then this is just the rules. Like if you just, from the table you showed us earlier with the summary, if you just plug in 0 to test your limit here, 1 over 0 equals infinity, it's positive constant or fixed number over 0. So.
Yeah, exactly. It's kind of like what I was referring to earlier today, where you have a fixed number on top and the bottom set it to 0. Now, we need to investigate this a little bit more. I told you not to worry about it earlier because we get into more detail with this. I'm about to get into more detail. Everyone needs to understand why the answer to this is infinity if we did not have the picture, okay? If we didn't have the picture, how could we tell that the answer is infinity? And this is one of the most fundamental ideas in this class. It's kind of like a number sense idea. So let's consider here this function f of x equals 1 over x squared. And the limit as x approaches 0 of that function. Okay, so let's start by looking at what the limit is as we approach from the left side of 0. Okay, as we approach from the left. Now, if we just try and plug in 0, we get 1 over 0. We know that already, right? That's what will happen if we try and just plug 0 in. But just consider what's actually happening here. Your number line looks like this. You have 0 here, and we are approaching 0 from the left. So somebody give me an example of a number that would be to the left of 0, but kind of close to 0. Anything you want?
Negative 0.01.
Okay, so you want me to pick negative 0.01. You might have said 0.001, but I'll just go with negative 0.01. All right, what would happen if I took that and plugged that into that expression, into that function? So what would happen if I did 1 over negative 0.01 and then squared? And do that on your calculator, see what you get. You plug this in, 1 divided by.
It approaches infinity because the closer you get to your zeros, it's always going to be a positive number because there's a square on the bottom, and then the closer you get, the smaller you're dividing 1 by, so it's just going to infinitely get bigger, right?
That's exactly right, but everyone here needs to understand that exact concept. That as I plug in numbers, right? As I plug in numbers that get smaller, right? So I'm going to tell you what this answer is. This should give you 10,000 if you plug that into your calculator. All right, so what's happening on top is you have a fixed number, right? And this number is small, isn't it? And what happens when you take a fixed number and divide it by a small number? Well, your answer should be a big number, right? You should get a big number as an answer. But what would happen if we take a number that's even smaller, right? Even closer to 0, like negative 0.00001. And we plug that in, 1 over negative 0.00001, and then square that. Let's see, I'll do that on my calculator. How many zeros do I have? 4? I get 1 with 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, oops, 10. There we go. Okay, so what is that, 10
It's
billion?
2 billion, yeah.
10 billion? So this is a conceptual idea that everyone in a calculus class has to understand. When you're looking at a fraction, right? If I have a fraction and my numerator is fixed, right? It's not moving, it's staying the same number. And the bottom approaches 0, which means it gets smaller and smaller and smaller and smaller. Then the fraction should do what? Get big or small?
Get bigger.
Get big, right? This thing should get big. This thing should become huge, big, right? Big, 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 big. Is that clear to everyone? Take any number and then just start dividing it by smaller and smaller numbers, and you're going to get larger and larger answers. The only thing that's kind of unknown is whether or not that answer is going to be positive or negative. And that is strictly determined by the sign of the numerator and denominator, right? If the numerator and denominator are both positive, your answer should be a big positive number. If the numerator and denominator are both negative, then your answer should be a big positive number. If one of them is negative and the other one's positive, then you'll have a ratio that's negative, so you should get a big negative number. Does that all make sense? Any questions?
Does this go back to the first thing we did? Or
Yeah,
back
this
to
is
that problem?
exactly, yeah, this is exactly that limit summary that I was giving you here. Okay, so when you're taking a limit, let's look at this. This may make more sense to you now. When you're taking a limit and you get fixed over 0, then you only have 4 possible outcomes. If your top is fixed and positive, and your denominator, now be careful with this. I'm not saying that that's 0. What I'm saying here is we are approaching 0 with positive numbers, right? We're approaching 0 with positive numbers. So as long as the numerator is positive and the denominator is getting smaller and smaller and smaller, approaching 0, but also staying positive the whole time, then your ratio should be infinitely big and positive. If we make the top a negative number and the bottom approaches 0 through little small negative numbers, then your ratio would then still be a positive infinity. If you change the signs on the top and bottom, either top positive, bottom negative, or the other way around, then your answer should be negative infinity. Yay? No? Yes? Good.
Right, and then the only reason we got positive infinity for the example is because it's an x squared, so negative times negative positive.
Or yeah, exactly. So when we go back and we look at this problem, I want us to look at this problem now that we've kind of discussed it a little bit. I want us to think about this problem in a more abstract way and start it all over. So if you're asked to find the limit as x goes to 0 of 1 over x squared, the way I would do this is first I'd figure out what's going on. Okay, so I plug in, I say, all right, the top is headed to 1, the bottom is headed to 0. This is bad, right? But it's bad, not bad, I need algebra. It's bad, I need to think about what's happening, right? So the top is a fixed positive or negative number.
Positive.
It's positive. 1 is a positive number, right? So this is a fixed positive number. Now, the bottom we know is headed to 0. We know that because it's headed to 0. The question is it headed to 0 through positives or negatives? Well, that depends on which side of the limit I'm coming in on, right? Which side does it say right here?
Both.
Both, right? But there's one element to this problem that eliminates us worrying about plus or minus, and what is it? What can you tell me about the denominator is what?
Squared.
It's squared, which means it's always what?
Positive.
Positive, right? This squared here is critical, because what this is telling me is that even though the denominator is headed to smaller and smaller numbers, because I'm squaring what goes in there, it's going to always come out positive. So I know that it's, oops, that's not this one. And no, it's not that. It must be small positive numbers, which means the ratio of 2 positive numbers should be an infinitely large positive number. So my answer would be positive infinity. And that corresponds to what the picture did, right? The picture went like that. Let's try another one. What is the limit as x approaches 0? This time I'm going to make it from a side, from the left, of 1 over x cubed. All right, so let's think about this. With any limit, we try direct substitution first. So what happens when I try direct substitution? Well, the numerator is just 1, that's not changing. The denominator, well, 0 cubed is still 0, so I have this. That is a fixed number, which is positive over something that's headed to 0. I still don't know if it's positive or negative. That I have to figure out.
Wouldn't it go positive, sir?
I'm
Would
going to
it?
say negative because
It's
it's a
negative.
cube.
Oh
So
wait, yeah,
it's-
yeah, it's odd, it's odd.
So it's cubed this time, right? It's cubed. Now, which side of 0 are we coming in from?
The left side.
Left side. So watch, I'm going to draw a little number line. Here's 0. Okay. I'm supposed to be approaching 0 from the left side. So the numbers that I'm plugging in here are really, really small negative numbers, aren't they? Like, for example, negative 0.00001 would be an example of a number that I could plug in. When I plug that in here and cube it, what happens to a negative number when you cube it?
Stays negative.
Stays negative, right? Stays negative. That means I can deduce that the denominator is headed to 0 through negative numbers, and therefore the ratio of these two should be a huge negative number. So my answer should be negative infinity. Make sense?
Mhm.
What if I change the direction which we approach zero? Let me do the same. Let's do the same problem. Limit x approaches zero from the right this time of 1 over x cubed. So I would say, I would go through this. I say, okay, top is headed to 1, bottom is headed to 0. Okay, that's a fixed number. It's positive over. Okay, on the bottom, I'm headed to 0. I need to figure out if it's through plus positives or negatives. I am on the number line. Here's 0. I'm coming in from the right this time. An example of a number that would be to the right of 0 would be 0.0001. If I plug that in here and cube it, it stays positive, right?
Yeah, it should theoretically get bigger, so we should have positive infinity for an answer.
Yeah. So, well, hold on. You said it gets bigger. What gets bigger? The ratio? The fixed over 0? Is that what you're saying?
Yeah, yeah.
Yeah. So you have a positive on top, and we can eliminate the negative because we know that when we cube a positive number, we get positive. So our answer should be positive infinity. One more question. What is the limit as x approaches 0 of 1 over x cubed? Brian, what do you think? Is Brian here?
Hey, I'm sorry, I was eating something.
Do you need me to come back to you?
No, I'm writing it all down. Are you asking for like, what are you asking for this one right here?
Right here. I want to know what's the limit as x approaches 0 of 1 over x cubed. We just did
So it would still be 1 over 0.
Mhm.
And so because you're approaching from both sides, it would be.
So from one side, what is it approaching? From the left of 0, what did we say it's approaching?
What do you wait? Whenever you're approaching 0, it's approaching from, or like it's the negative. Like you mean the
Well,
negative?
I think what you were saying is that because I didn't put plus or minus, I think what you were saying is that means we have to look at both.
Yes.
Okay, and we already did that, right? Look at the previous two problems. We already did this from the left, and from the left, what was our answer?
A negative infinity.
Okay, and from the right, it was what?
Infinity.
Okay, so are they the same answer?
No.
Okay, which means this limit
Can't. It's
yeah, you're there.
What? It's undefined.
Does not
But doesn't exist.
exist. Okay, there we go. Does not exist. And that's because the left and right hand limits are not equal to one another. The problem that we did earlier with the x squared, this answer does exist because both the left and right limits give you the same result. And the only reason they give you the same result is because it was a squared. And so it didn't matter which side you're coming in from. You're squaring the bottom, it's always going to give you positive.
And this goes for any even or odd exponent. Odd.
Yeah, pretty
more than
much this would work for any even or odd.
Yep.
Okay.
So if
if
it was asking for if it's a odd exponent, it's asking for both. It's basically always going to be, if it looks like that, it's going to be does not exist.
I'm gonna say if it's strictly a power function like 1 over x to the n, then yes.
Yeah.
Yes. Let me give you all a whole new problem, all right? Limit x approaches 2 of x squared plus 4. X squared plus 4 over x squared minus 4. Let's approach 2 from the right. All right. Cruz, are you here?
Yes.
How's it going, Cruz?
Good.
Okay, are you understanding so far?
So far, yes.
Okay, so on this one, Cruz, what is the first thing that I've suggested you do for all limits?
To plug it in.
Plug in. Okay, so what would happen if we plugged in 2? Just tell me what we would get up top and what we would get on the bottom.
You would get 8 on the top
Mm-hmm.
and then 0 on the bottom.
0. Yep, everyone see that? So we have to be real careful. We are not getting 0 over 0 like previous class, okay? 0 over 0 means algebra trick, but when we see fixed over 0, we immediately know that it's going to be this thing where we have to analyze whether or not we're getting pluses or minuses, and it's not the algebra trick thing, okay? It's a completely different idea. So Cruz, this is fixed over 0. Can you tell me, Cruz, what the top is? It's fixed, but can you tell me whether it's positive or negative on the top?
It would be positive, wouldn't it?
Yeah, it's 8, right? 8's a positive number, right? So that's pretty straightforward. We don't have to think about that too much. But we do need to consider the bottom. Is it positive or is it negative, right? That's the thing we have to figure out. So what I suggest you do, this is what I like to do, is I like to draw a number line, okay? I like to put the number I'm headed to. I'm headed to 2, and I'm headed from the right-hand side, okay? Now, I already know that as I plug the number 2 in, I'm going to get 0 on the bottom, right? And if I plug in numbers close to 2, I know the bottom number is going to be smaller and smaller and smaller and smaller. It's just a question of whether or not it's a positive or negative. So Cruz, give me any number you can think of that's pretty close to 2, but to the right of it.
It's the 0.01.
Look at where not at 0, we're at 2. Careful.
Oh, sorry.
Right. So it's a little to the right of 2.
1.1.
That's on the
I
left
mean,
side.
2.1. I'm sorry.
2.1. Okay, let's go with 2.1. All right. That everyone agree that that number is to the right of 2?
Mhm.
Is it close to 2? I
Well,
mean, this is
close
what
enough, I
we
guess.
said last class. Like, is that close? Could we get closer? We could get
Infinitely
closer,
so.
but it doesn't matter, because all we want to know is if I took that number and I plugged it in right here, what would 2.1 be? Well, it would be bigger than 4, wouldn't it?
Positive.
And I'm going to subtract 4. So that difference should be positive or negative. What would it be? If I took 2.1 and squared it and subtracted 4, should I get a positive or negative number?
Positive.
Positive.
Right? And that tells me that as long as I'm picking numbers to the right of 2, I'm always going to get a positive answer on the bottom, not a negative. And so a positive over a positive should give me an answer of positive infinity. Cruz, does that make sense?
Yes.
Okay. How would the problem change? Let's go to Justin now. Justin, how would this problem change if I now asked you to come in from the left side of 2 as opposed to the right side? So is Justin here?
I am here.
There you are, Justin. Are you following okay, Justin?
I don't think I'm following with the question that you just asked me. I don't know what you mean.
I guess what I'm asking is, I'm going to change the limit, right? So instead of coming in from the right of 2, I want you to come in from the left of 2. So let's see if that changes the answer.
Oh, okay.
So let's start out first by just plugging 2 into the top and bottom. So what would we get, Justin, if we just plug 2 in to the top and the bottom?
Would it still be 8 over 0, right?
Yes, still 8 over 0. And Justin, that's still a fixed number
Mhm.
over 0, right?
Yes, sir.
And the numerator is still 8, so it's still a positive number up there. So you just need to tell me, Justin, whether or not the bottom is positive or negative, headed to 0 through positives or negatives.
Okay.
So you grab the
You
number
do.
line. Go ahead.
Do you just do the opposite what we did last time? So you
Yeah,
check
so
with
we
like
come in this way.
1.9.
1.9, is that what you said?
Mhm.
So if we plug in 1.9 and we take that and we plug it in here, Justin, 1.9 squared, that's not quite going to be 4, is it? It's going to be a
No.
little bit short of 4. So
Yeah.
when I subtract 4 from it, I should get what type of number?
Negative.
Negative. So I can eliminate the positive, and I know that I'm going to get a negative down there.
Okay.
And that's it. So I know that a positive on top divided by a negative on bottom should be negative. And we already knew it was going to become infinite because we have a fixed number over something going to 0.
Huh.
Good. Questions there?
So just from here, we can assume that limit of x as it approaches 2, it does not exist.
Exactly. So if I change this problem, I took the plus away here, right? Then the answer would be does not exist. But you would have to go check, right? You would have to actually go check both sides to answer that question.
Well, yeah, assuming we hadn't just done all that.
Yeah,
like that,
assuming
yeah.
we had not, right? Assuming we had not, you would then go have to check both sides. Okay. Let's do another one. I'm going to give everyone a minute or two to work on this on your own and see how far you can get to it. Let me give you 2.5 minutes. See what you can do.
I'm having, never mind.
Just to be clear, everyone, we're approaching -2 from the left. Okay, I think that's enough. Jorge?
Yes, sir.
So let's see. What do you think?
I thought I had it. Then I looked at it again and I was like, oh no, I'm chalked here. So the bottom, was that right? It's -2 -2. So that's giving you a fixed number, no?
Yes. What? So the bottom is headed to where?
To -2.
-2 minus 2.
Yeah,
Right? Which would be -4.
correct.
And the numerator is headed where?
-20.
Is it -20, everyone? I don't know.
Negative 12.
Negative
so-
12, yeah.
Okay.
I got negative 12.
Negative 12, okay, negative 12, so no problems,
see
right?
Yeah.
It's just 3. Okay, so there's a moral to the story here. Be careful. Don't get ahead of yourself. Don't start doing things that aren't right because you're anticipating something's going to be a certain way. This limit had no problems because we never had 0 over 0 and we never had division by 0, right? We didn't have fixed over 0. So you don't go do any work. It just spat out a number, boom, there it is. That's the limit. Now, that was just to make sure everyone doesn't start getting the carriage in front of the horse. Let's change the problem. Change that to a +2 on the bottom. Okay, change the problem to a +2. And then things are going to not work. So we'll work through that. Let's work through it together. So, yeah, we'll go back to Jorge. Is Jorge still here?
Yes.
Okay, so Jorge, now that I've changed the problem to +2 on the bottom, the numerator should still go to negative 12, right?
Yes.
But now the denominator is headed where?
To 0, sorry.
To 0. Okay. So that means our numerator is a fixed number. Is it fixed positive or negative on top?
Negative.
Negative. That's the first time we've had that. And then over 0. And now, Jorge, it's up to us to determine whether or not it's headed towards 0 through positive or negative numbers.
But on top, wouldn't it be
Negative.
negative?
Is the top what?
Because I thought we're doing if it was going to +2.
No. I changed this to
Oh.
a +2 right here.
Oh, never mind. Sorry, my bad.
No, it's okay. It's okay. Okay, so Jorge, we're gonna draw a number line, right?
Yeah, it's coming in from the left side, so it's still going to be negative, and it'll be negative and negative top and bottom, so it's still infinity, I think.
Okay, hold on. Slow
Wouldn't it be
down. Slow
positive?
down. So you're coming into the left of -2, right?
Yes.
That means you need to pick a number here as a sample to plug into here to see if this together would give you a positive or negative number. I think we may have lost Jorge.
Oh, can you hear me still or no?
I can hear you. I
Okay,
can hear
yeah,
you.
sorry, the camera goes away
Okay,
sometimes.
we don't need to see you. It's okay. So this is a very tricky problem. Okay, Jorge, I need a number to the left of -2.
Okay, so negative 2.001.
Okay, -2.001. People will forget and they'll put like -1.99. You have to remember where -1 is. -1 is here, 0's here, -3 is here. So good. Jorge didn't get caught there in that trap. To the left of -2 is -2.001. Right? -1.999 is to the right of it. Okay, so just be careful. All right, so now Jorge, when we plug this number in right here and add 2, we will have a very small what?
Negative number.
Negative number, which is what you said. So you may have already gone through all that, but I think everyone just needs to see that just to be clear.
Yes,
So
sir.
that's negative. All right, so what's our final answer, Jorge?
Infinity.
Positive, right?
Yes.
There we go. Good.
I did the 1.99.
All right, so this is a lot about just kind of like an understanding like number sense. Like if you have a fixed number over something gets small, we know that ratio gets big. It's just a matter of determining whether or not it's positive or negative. And of course, if we have to check both directions, then they have to match. Okay, they both be infinity or both negative infinity for the limit to exist. All right, good. That went well, I think. Let me go back to the notes here, see if there's anything else I want to go through here. Okay, so yeah, I'll just mention this. You've actually studied this before in college algebra. These were called vertical asymptotes. So when you were looking at functions, specifically rational functions in college algebra, you were looking at functions where the function would go up or down, and there's like a vertical barrier it couldn't cross, right? Those are called vertical asymptotes. In a calculus class, those are these infinite limits. It's where our graph, as we approach a number, from one side it dives down, maybe the other side goes up, or maybe they both go down or both go up. Okay, anywhere you have a vertical asymptote, you're going to have an infinite limit. Okay, so we call, this is the algebra definition, the line x equals a, that's a vertical line, is called the vertical asymptote of some function y equals f of x if any of the following are true. If you approach a from the left, if it goes to positive infinity, well, you've got a vertical asymptote there. If it goes to, if you approach from the right and it goes to positive infinity, you have a vertical asymptote. So all of these different combinations just say it doesn't matter, like left, right, you're either getting positive or negative infinity, something's happening. There's where you have vertical asymptotes. Okay. Let me draw you a quick function here, just to make sure you understand that concept. This is going to be a little bit weird. So I'll make the first one easy. So here's A, and I'm going to draw a graph where at A, I have this happening. To the left, the function goes like that. And to the right, the function goes like that. So Brianna, are you there?
Yeah, I'm right here.
Oh, Bree, right? You changed that or no? You know what
Okay.
happened?
Yeah.
Last class, I forgot to click save on my file, and so I lost everything. So if I did that to Bree, I lost it. It's, yeah. Oh, well. I thought I had saved it. No, maybe I did. No, I'll have to look. Okay, so Bree, do we have a vertical asymptote at A? If you look at this graph, yes,
Yeah.
right? Why?
Yeah. Because it's both of them are approaching A. Did I
Okay.
get that right?
So if we look at the definition of a vertical asymptote, to say that x equals A is a vertical asymptote, that happens if any one of the following are true, right? So when you look at this, all we need is that when you approach it from one side,
They go to infinity.
or a negative infinity, right? So here you have like more than you need, right? It's actually from both sides. Now compare that to this. Compare that to this. What if we had a function that did this? Here's A. And it went like this. But at A, I defined it to be a point and come out this side like that. Do I still have a vertical asymptote at A?
I'm gonna say yes by.
But
That's
only
right.
for one of them.
Yeah, because it says if any one of these are true, okay? All we need is that from one side of A, you're taking off to infinity or negative infinity. If on the other side you're not, that doesn't matter, okay? That doesn't matter. We still have.
As long as one.
As long as one.
Okay.
Now, in college algebra, all you ever study are rational functions, and those always have this happening. You don't have what I just showed you, all right? Okay. All right, so now's our time for our break. Let's take a 10-minute break, and we'll be back at 2:40, and then we will go for about, what, 50 minutes after that? We'll do the second half of this section, all right? All right. Infinite limits.
I fell into the trap. I did negative 1.99. It feels bad.
Well, that's why I show it, because I want to make sure that you pay attention to that. That's all. All right, here we go. Take a break.
Bree, I hope that's not coffee at 2:40. I can't drink past like 12:30 or I'm just
It
wired.
is. It's coffee. It's from like way earlier this morning. It takes me forever to drink it.
Cold coffee on top of that. Oh my goodness.
I've gotten used to. I have a kid, so cold coffee is my life.
Keep trying to catch Brian at the right time. I spotted a bunch of Pokemon stuff, but I can't tell if there's anime there too or not. I think I see a Your Name poster, maybe some other
Oh
stuff.
yeah, a bunch of anime statues. I got an Itachi one, a Toshiro Hitsugaya, and Nico Robin.
Is that your room?
One Piece fan?
Yeah. Oh, I love One Piece. It's like my favorite shonen.
You're like a long lost. Oh my gosh, I'm so glad I found you, bro. I'm like, I cry internally every time I talk to people about anime. One Piece is too long, but they've watched all of Naruto and Bleach. It's like, okay, I'm the basic math here.
Yeah. On my back wall, I got a bunch of the old shonen jumps, like panels and stuff. You can see it back there. But no, I play Pokemon competitively.
Nice. You're muted, by the way, sir, if you're trying to talk to us.
No, I was just listening.
Oh, okay.
Okay, y'all ready? Let's get back to the real fun stuff. All right, so this section I said again has two types of limits in it. The one we just looked at was where we try and take a limit and we realize that the denominator heads to 0 while the numerator remains a fixed number. Now we're going to change things and we're going to have this concept called limits at infinity. Not infinite limits, limits at infinity. So don't confuse the two. And what's going to change here is that, you know, up to this point, every time we've been letting x approach a number, it's been headed to like, you know, 0 or 2 or -2, and maybe from the left or from the right. Now what we're going to do is we're going to allow x to head to infinity or to negative infinity. Now, what does that mean visually, geometrically? So let's take a look. So if we take a look at this function, f of x is 1 over x. That's the graph that you see here. Then if I want to know what's happening as x goes to infinity, in other words, the limit as x heads to infinity of that function 1 over x, then what I'm saying is, what is the output of the function doing as x gets bigger and bigger and bigger? So we can see this visually if we look at this dot here and start moving the x value. Oop, that moved a little too fast. Start moving the x value out to the right. Can y'all see what's happening to the y value? No, it's not very good.
Smaller.
It's getting smaller though, right? It's getting smaller and smaller and smaller. Let me follow this. Okay, there we go. That's better. So right now, if we plug in x is 7, 1 divided by 7 would be 0.142857. If we keep going to the right, okay, so now x is 10, we get 0.1, and we keep going and going and going, and I can keep doing this, going out to 100. See what's happening to the function's value? It's getting smaller and smaller and smaller. It is approaching what value? What is the function's value approaching?
Oh, the function, I guess it's approaching infinity. 'Cause it's,
X is approaching infinity, but the function itself is approaching 0.
0. Okay.
Right? It's approaching 0. Now, again, let's think about this big picture. What's happening here? We have on the top, right? We have a fixed number, right? And on the bottom, x is becoming infinitely large. So the same idea that we had before. Earlier, just the section right before this, we had a fixed number and the number on the bottom was getting small, right? Going to 0, and that ratio became huge. But now we have a fixed number over something that's getting big, right? So that ratio should become small. So those are almost like inverses in one another, right? Fixed on top, bottom goes to 0, ratio becomes infinite. Fixed on top, bottom gets big, ratio gets small. And so that's what off our, where's that?
so that's just the only difference. One is an infinitely bigger number. The other one is we're approaching no number, a 0.
That's right. So if we go back to this summary that I have here, what I'm talking about now is this bottom corner scenario. If we take a limit and the top is fixed, and it does not even matter whether or not the top is positive or negative, it makes no difference. If the top is fixed, then the bottom gets infinitely big, then the ratio will always go to 0. This is kind of the easiest case there is because there's nothing you have to check with signs. It's just fixed over big heads to 0. All right. So we'll do a couple of examples here.
Question though, we're only checking from the right because it's approaching infinity, not negative infinity. So it only is going out that way.
Well, we can go to negative infinity too, but if we go to negative infinity, we still have the same scenario because the top is not moving, right? The top is fixed and the bottom gets big but negative. So if it's big and negative, you're still going to get a really small number. It might be positive, it might be negative, but it's small. It's approaching 0.
So then it's just the infinity symbol or the sign of the infinity doesn't matter.
This doesn't matter. Yep.
Okay.
Okay. So let's see here. We have a property here. This is an important property that says that if we have if we have 1 over x raised to any power, doesn't matter as long as the power down there is a positive integer. So this is 1 over x or 1 over x squared or 1 over x cubed or 1 over x to the 4th. Doesn't matter what the power is. That whether or not we go to infinity or negative infinity, these limits will go to 0 no matter what. And you can see it from the picture here. This is what we're looking at right now is 1 over x. Do you all see that as we go to the right, as x goes to positive infinity, does everyone see that the function is approaching 0 asymptotically? It's getting closer and closer. And as we go to x goes to negative infinity out the left, again, it's approaching 0. Now they're negative numbers, tiny little negative numbers, but they are approaching 0. That does not change if I change this to 1 over x squared. See, the picture stays the same. I mean, not the whole picture, but the edges of the picture look the same. 1 over x cubed, picture at the two ends looks the same. And that would work for any power of x. Now we're going to use that property in a moment, all right? Any questions on that?
Will we ever have anything to do with a negative exponent in this class?
So if it was a negative exponent, think of it this way. If I gave you f of x was 1 over x to the negative 2, and I asked you what's the limit as x goes to infinity of that function, then isn't negative 2 on the bottom, a power x to negative 2 on the bottom, couldn't you just flip that back up and put it up on top as x to the positive 2? Aren't those the same?
Oh yeah, that's right. Mm-hmm.
And now think about what happens here. If I have a number, right, like imagine this x right here is just going to get bigger and bigger and bigger and bigger and bigger and bigger. And you're going to square it. That's going to make it bigger and bigger and bigger, right? Wouldn't that mean that this thing just heads off to infinity? It just gets huge. So that's why we're not looking at the negatives, Cody, is because if we did negatives, it would flip it up and then it would just become infinite and there wouldn't be any real work to do there.
Okay, fair enough.
All right, now let's do an example. Let's find the limit as x goes to positive infinity. We'll start off easy. X plus 1 over 2x plus 3. All right, Rogelio, you there?
Yes.
Okay, how's this going for you? Oh, is it Roger? You want me to do Roger?
I mean, whatever's fine. It doesn't really matter to me.
Do you prefer, you have Roger on your Zoom screen, so I can change it real easy in my roster.
Okay, yeah, that's fine.
Roger. All right, Roger. Let me save this. Okay, so Roger, how do we calculate limits? Anytime we're trying to do limits, what's like that first thing you want to do?
Plugging in, what was it?
Yeah, just plug in the X, right?
Yeah.
Plug in the X. Now, for the first time, we can't plug X in. I mean, really, X is headed to infinity, right? You can't really plug infinity in. But you can think about what would happen, can't you? Like,
Yeah.
Roger, if I took a number, this number X, right, and I were to imagine that it becomes infinitely large, if I add 1 to that, right, then this whole thing together is still some infinite, becoming infinitely large, isn't it?
Yeah.
So you could say, Roger, that the numerator is headed to infinity. Do you agree?
Yes.
Okay. Now the denominator, this is headed to 2 times some huge number plus 3. But 2 times some huge number is still some huge number plus 3. But that's still just some huge number, right?
Yes.
So you could tell me that the bottom is also headed to infinity. And this is the first time we've had this. It's the first time we've seen infinity over infinity, right? Infinity over infinity. Now, if we go back to our limit formulas here, we've focused a lot of our attention today on this, and I just mentioned to you this, but now we actually are looking at this here in green, infinity divided by infinity. And whenever we see infinity divided by infinity, we are going to have to use some algebra or some trick, right? That's what we're going to need to do. So, all right, algebra or some trick. Let me write the problem down here again. The algebra that we did earlier, right? When we were getting 0 over 0, right? When we were getting 0 over 0, last class, 0 over 0. We were doing like factoring, we were doing conjugate, we were trying to get something to cancel. That's what you were doing in your homework, right? You're trying to factor or manipulate, and eventually something canceled out and then everything was good. Whenever you have infinity over infinity, you do not normally want to do any factoring. What you want to do is exploit that property that I just showed you in our notes. We want to exploit this property right here, that if we ever see a fixed number over X to any positive power, that we're guaranteed that this will go to 0. So what do I mean by exploit that property? Let me show you. Okay? I'm going to show you how we're going to exploit it. What I'm going to do is I'm going to look at this fraction, and I'm going to look at the denominator, and I'm going to look for the highest power of X that I see in the denominator. Okay, so I see that X right there, and it's to the first power, right? It's to the first power. Now, I'll explain as we do this why I'm going with the highest power in the denominator, not the numerator. I'll explain that after we get through an example or two. And I think it'll start to make sense why we're doing it. So I see that the highest power of X in the denominator is X to the first power. So what I'm going to do now, something kind of tricky, I'm going to take this expression and I'm going to introduce a 1 out front. The 1 that I'm going to introduce is going to be 1 over X over 1 over X. Now, the reason I'm using 1 over X is because this was an X to the first power. Had this been X squared, I would have done 1 over X squared, 1 over X squared. Had this been X cubed, I would have done 1 over X cubed, 1 over X cubed. Now, let's see why I did that. Okay, I'm going to now multiply those through. So I have to distribute like that. And let's see what we get.
Wait, can you repeat again where when you said if X was raised to a different number, what would happen? Because it kind of cut off on my side.
Yeah. So if X is raised to the first power, I'm going to go 1 over X, 1 over X. If it was X squared, I would do 1 over X squared, 1 over X squared. If it was X cubed, 1 over X cubed, 1 over X cubed. And now as I work through this, I think hopefully you'll see why this works. So let's do our distribution. 1 over X times X gives us what? This top one? 1 over X times X? What's that?
Give us 1.
1, okay. And then plus, what's 1 over x times 1?
1 over x.
1 over x. Okay. And then on the bottom, let's see, when I do 1 over x times 2x, the x's cancel. I'm left with a 2. And then when I do 1 over x times 3, I'm left with, well, 3 over x. Any questions on that? That's just distribution through. Does everybody see that these two terms right here fall into the category of this property right here? That, well, they don't both have a 1 on top, but it doesn't matter. This is fixed on top, fixed, right? Over something that becomes infinitely big, that should go to 0. I want you to just think about that. Fixed number, the number 1 divided by a number x that's getting huge. 1 divided by a huge number becomes very small. 3 divided by a huge number becomes very small. So if I now take the limit, right? Let's let x go to infinity, right? Let it do its thing. This thing's going to head to 0. This thing's going to head to 0. And the only thing left is going to be the 1 on top over the 2 that was out front. And that's your answer, 1/2. If I were to graph this, where are my decimals going? What was it? X plus 1 over 2x plus 3?
Yes, sir.
Okay, if I graph this, then let me also graph y equals 1/2. That's this blue line, horizontal line. I'll make it dotted, so looks a little different. There we go. Okay, so can you see that as I go to infinity, as I go out to the right, can y'all see that my function is getting closer and closer and closer and closer to that dotted line, 1/2, right? That's exactly what we just determined, but we did it algebraically. Can anybody see why I'm always going to be looking at the highest power of x in the denominator? I'm always curious to see if my students can see why it is that this should work for us every time.
Because it gets rid of like the having just x, and not being able to, like, how you can't add like infinity plus 1. Well, that removes that problem of getting infinity plus 1. Because if you like multiply, you get 1 instead of just x when it was at the beginning of the problem.
Yeah, I think you're onto it. So just think about if we had an expression here, okay? Let's say the top has a bunch of things added together. Who cares what they are? Those could be subtractions, okay? We could have 2 of them, 3 of them, 4 of them, 5 of them. Doesn't matter how many we have, okay? Doesn't matter. If we look and we find that this one right here had the highest power of x, okay? Let's say that that one right there had the highest power of x. And let's just say for the sake of demonstrating, this is x to the n. Then if I come over here with 1 over x to the n, 1 over x to the n, when I distribute that through, think about just the bottom first, okay? When I distribute that here, here, and here, all those red ones, what can you tell me we're going to get? On just the red ones, we're going to get
0.
Well, after the limit, won't we? But when we do the algebra like through here, because this is the highest power of x, all of these 3, this one, and this one, when we multiply through, will all wind up having an x in the denominator. Because the highest power, we're going with the highest power of x, right? So these would all have powers that are less than that. So when I divide through it by it, I should have x's left in the bottom, which means that all of those, after I take the limit, will go to 0, 0, 0, right? All of them should, except this one in yellow. That one, the only thing that will be left will be what?
Exponent? Or the thing
coefficient.
Yeah.
The coefficient, the number in front, whatever the number is that's in front of this will always be what's left on the bottom when I come through with the 1 over x to the n. Do y'all see that? So at the end of the day, what I'm going to wind up with when I do the limit is on the bottom, I'm just going to wind up with a number always. And then I don't care what the numerator does. If the numerator goes to 0, then my answer is going to be 0 over a number, and that's 0. I mean, sorry, yeah, 0 over a number, that's just 0, right? If the top happens to go to infinity, well, then infinity over a number is just infinity. So we're trying to exploit a weakness within the expression, and the weakness is to find the highest power of x and then come through with the 1 over it. We'll do another one. Limit x goes to infinity, x squared minus 3x plus 1 over 5x cubed. Let's go squared plus 1. All right. Marissa, you there?
Yes,
There you are. How's it going, Marissa?
I'm good. How are you?
Okay. All right, so Marissa, let's talk about the behavior of this thing. Let's talk about the numerator first. So Marissa, where is x squared headed if I'm letting x go to infinity? Sorry, I didn't hear you if you said something.
Sorry, to infinity.
Infinity, okay, so infinity squared is basically infinity. And then you're going to be subtracting from that 3 times infinity, which should be what?
Negative infinity.
So minus infinity and then plus 1, right?
Mhm.
Okay, we've run into our first problem, okay? Problem meaning our first issue that we didn't run, well, not our first one, we've had a lot of issues in this class, but our first kind of weird situation with this type of limit. And that is this, Marissa, infinity, take away infinity. You may be tempted to say that's 0, but you can't, because all we're saying is that this first one is becoming infinitely large, and we're subtracting something that's becoming infinitely large also. But since these are not numbers, you cannot tell me that the answer is 0, right? So right now, Marissa, do you understand that this is kind of an open question?
Yeah.
Okay, so let me help everyone resolve this. When it comes to those two expressions, x squared and 3x, which of those two expressions, I'm going to stick with Marissa here. Marissa, which one of those two expressions do you think dominates the other one if we're plugging big numbers in?
The one with the higher exponent.
The highest power, the one with the highest power, right? X squared, if I take a number and square it, that's always going to be bigger than 3 times that number, right? So, and the bigger the number gets, the more of an impact that squaring has. So the x squared dominates this 3x, which means that this will become whatever the x squared was doing. So this becomes infinite. That's important, right? Because generally speaking, infinity minus infinity is not 0, okay? Generally speaking. And then plus 1, right? We still have plus 1. So the top, Marissa, is going to infinity. The bottom's easier, Marissa. Where's the bottom headed? The whole thing. Infinity. Okay, so we have infinity over infinity. So we're sticking with Marissa here. Marissa, anytime we see infinity over infinity, we're thinking bad. We're thinking algebra, some trick. And what is the trick, Marissa? What's the trick we're going to use here?
Can you repeat the question one more time, please?
So we know we have infinity over infinity, just like we did before, right? Anytime we see that, we're going to be doing some sort of algebra or trick to do this. But with infinity over infinity, it's a very special trick. And what is the trick that we're going to try?
I'm not too sure, to be honest.
Okay, that's okay. All right, does someone want to help?
You're going to multiply the the whole thing by the highest term on the denominator.
Yeah, your reciprocal of your highest exponent.
Yeah, so we're going to go identify, Marissa. We're going to go look in the denominator for the highest power of x that we see, which is x squared. And then we're going to multiply the top and bottom, not by x squared, but by 1 over x squared. 1 over x squared. We do it on the top and the bottom. And then distribute through. And this should get it for us. All right, this should. I'm going to move this. I'm out of space, so I'm going to have to go to the next page here. So we want to distribute here, 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 here. Limit x goes to infinity. Okay, I'm going to go quickly through this. On the top, 1 over x squared times x squared is 1. Okay, 1 over x squared times negative 3x is negative 3 over x. One of the x's cancels. And then plus 1 over x squared times 1 is 1 over x squared. And then on the bottom, we have 5x squared times 1 over x squared is 5. And then plus 1 over x squared. Are there any questions on where any of that comes from? The whole point of this is that anything that we have left that has a number over x to a power should go to 0 when we take the limit. So we have a bunch of things that are about to vanish. This is going to vanish to 0. That's going to vanish to 0. That's going to vanish to 0. And the only things left are going to be a 1 up top and a 5 on the bottom. And so you get 1/5.
What's the name of the rule with the highest power?
There's no name.
Okay.
Not that I'm aware
I had a
of.
question.
Yes.
Why do those vanish to 0?
Why do they? Okay, because we're letting x become infinite, right? And so as x gets big, think about what happens. 3 over a huge number becomes infinitely small, right? Smaller and smaller. The bigger x gets, the less and less this contributes to anything, because it becomes like, this becomes, I mean, think about if x is like a billion raised to the billion power, like 3 divided by that is going to be like 0.00000000000, you know, way out, right? It's really essentially 0. And this is essentially 0. Yeah.
Thank you. Appreciate it.
Yep. I'm wondering if anyone remembers from college algebra that if you're given a function, like let's say I gave you this function in college algebra. I wonder if you remember from college algebra that when you study these types of functions called rational functions, that we look to see what the horizontal asymptote is. The horizontal asymptote is what's happening at the edges of the function, of the rational function. And one thing that you were taught, maybe, depending on your professor, is that if you compare the degree of the numerator and denominator, the highest powers of x, that if they're the same on top and bottom, then the horizontal asymptote will always be the leading coefficient of this one divided by the leading coefficient of that one, the 1 over 5. Do y'all remember seeing that in college algebra?
Yeah, when you mentioned it, yeah, but now I'm trying to remember what happens if the denominator is like a power higher or something like that.
Yeah, so if the denominator is not the same power, then it's something else. But if they're the same, then all you really care about are those two numbers. Do y'all see why now? Y'all see why? I mean, if they have the same power on the top and bottom, right, then you're going to come through with the 1 over x squared. And then when you hit that top polynomial with the 1 over x squared, all you're going to get is its coefficient, 1. And then the bottom, you're going to be left with that 5. And everything else is going to vanish to 0. So all that really matters at the end of the day is those coefficients. Now, that's the way you do in college algebra. We're in calculus now, so we're actually doing a limit. All right, let's do another one. How about this? Limit x goes to infinity of x cubed minus x plus 4 over x to the 4th minus 4x squared minus 10,000. Let me let you think about it. See what you can do with this, okay? I'm going to bring up my little clock here. I'm gonna give you like 2.5 minutes, 2 minutes, something like that. Where my clock went? There we go. Okay, I went ahead and started working this out. So as x goes to infinity, x cubed minus x plus 4 becomes infinite. The reason x cubed becomes infinite minus another thing that becomes infinite, but x cubed dominates x. So this should become infinite plus 4 is still infinite. And then same thing here, x to the 4th minus 4x squared, those both become infinite and you're subtracting, but x to the 4th dominates 4x squared. Because squaring something does make it bigger, but to the 4th power, that's even more powerful. And so we get infinity over infinity, identify the highest power of x on the bottom, multiply top and bottom by it, distribute through. And now when I take the limit, everything vanishes to 0. Well, anything that has x in the bottom goes to 0. Do you have any questions on that? Anyone need clarification on any of that? So that's going to go to 0. 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 And so what I'm left with is up top 0, and on the bottom 1. And so your answer is 0.
This is just because since there's more exponents in the bottom, essentially it's going to get more powerful if you plug infinity in. So the one on the top, it'll be smaller. So kind of works out that way.
Yeah. So basically the bottom is dominating the top,
Right.
squeezing it down to nothing. And again, if you think back to college algebra, when you're learning about rational functions, they tell you if you compare the degree of the top and bottom, if the degree on the bottom is bigger than the top, they tell you that the x-axis is your horizontal asymptote. And the x-axis is y equals 0. That's exactly what it is. So that's why it happens. Does anyone remember what happens when the numerator's power is bigger than the denominator? So what would happen if I did something like this?
Isn't it infinitely bigger?
1 over x cubed plus x. I'm going to work quickly through this. Infinity over infinity. Come through with 1 over x cubed, right? 1 over x cubed.
Yeah, was it just 1?
What you mean in college algebra?
Yeah.
If your numerator's degree is bigger than your denominator's degree, you have no horizontal asymptotes. There are none. It just means that your graph doesn't flatten out at the edges, which you're about to see why. Because remember, I did the highest power of x on the bottom, right? So when I distribute through, let's see what we get. Limit x goes to infinity. We have on top x plus 1 over x cubed. And on the bottom, we have 1 plus 1 over x squared. So distributing here to here, we're still left with an x right there. Here to here, that, and on the bottom we have a 1, and then the x is canceled, we just get 1 over x squared. We have 2 things that vanish now. That goes to 0, that goes to 0. Where's the numerator headed? Well, where's that headed?
Infinity.
It's up, yeah, it's going bigger.
Right? Infinity over what?
1.
1. That's just headed to infinity. So I'm going to graph this just so you can see it, like just to verify. If we were to take, I'll put that back up there in a second, but if we were to take x to the 4th, whoa, that's not working. If we were to take x to the 4th plus 1 and divide that by x cubed plus x, you can see here that as we let x go to infinity, right, as we start to move out this direction, the graph just takes off, right? Just takes off to infinity. We don't have a horizontal asymptote. And that's because the degree of the top is bigger than the bottom. Questions? All right, now it's time to throw a little wrench into it. Limit x goes to infinity of 3x plus 1 over the square root. Ooh, the square root of x squared plus x. Okay, so now we have stepped away from college algebra. You never looked at a graph like this in college algebra. This is not a rational function, because even though the numerator is a polynomial, the denominator is not. So can we do it the same way? Well, yes and no. All right, yes and no. We can look at the denominator. Well, oh, sorry. We should probably check that this, does everyone agree that goes to infinity over infinity?
Mm-hmm.
Right, like infinity times 3 plus 1 is infinity. Infinity squared plus infinity is a huge infinitely large number. The square root of an infinitely large number is still infinitely large. So we do have infinity over infinity. So we do want to be doing some algebra. We do want to come out front with something, okay? But the thing is what, okay? That's the tricky part to this problem. So you ready? Pay attention to this. I'm still going to identify the highest power of x I see here, which is x squared. But I am not going to come through with 1 over x squared on the top and bottom. I'm not going to do that. And the reason why is because I have a square root in my way. Do y'all see that I have a square root in my way?
So it'd be 1 over x?
So it will be 1 over x. Why?
It's the square root of a square is just the original. So square root or x squared, a square root of that is just x.
Yeah, so there's actually multiple ways you can look at it. Here's the way I like to look at it. Okay, hopefully this makes sense to you. Go back to when you were learning square roots, right? We all know the square root of 4. Well, that's just 2, right? And that's because when you do square root of 4, it's 2 times 2. And so for every pair that you see in here, you can represent it. You can take it out. So like if I have the square root of 8, that's equal to 2 root 2, because you can rewrite 8 as 2 times 2 times 2. And for every group of two, you can pop it out as the 2 out here. So for each like pair on the inside of the root, it can come out. Let me say that again. Back when we're learning roots, if we have the square root of x cubed, this becomes x times the square root of x, because we have 3 x's in here. And so for every 2, we can pop 1 out, right? Which leaves us with 1 still in here. That's what hopefully you've learned in the past, you feel comfortable with. What I want you to think about is the reverse operation. If you have something outside of a square root, like x, and you want to push it into the root, then what happens to it when you push it in?
It's doubled.
It gets squared. Not double. Double would mean
Sorry.
multiplying by 2, but I know I know what you meant. But when you go in, it gets squared on its way in, right? So if I asked you to take this expression, push the x in here, it would become an x squared, and then it would hit the x and become your x cubed. So when I'm out here trying to figure out what to multiply by, I'm thinking that I need an x squared to cancel. So that means I need a 1 over x squared to wind up in here, which means I'm going to put a 1 over x here and a 1 over x here, because when I put the 1 over x and I push it into the root, it gets squared and becomes a 1 over x squared, which would then distribute through and kill off the x squared. That's the way I like to look at it. There's different ways you can visualize it. Does anyone have a question on that? So distribute top and bottom. Now on the top, nothing gets squared because there is no square root here. So that just gets distributed. So we're going to have limit x goes to infinity. On top, we have 3 plus 1 over x. On the bottom, the 1 over x goes inside, becomes a 1 over x squared, and then distributes to both of those. That should leave you with 1 over 1 plus x. The step I'm not showing you is this. When that 1 over x goes under that root, it gets squared on its way in, square the top and bottom, and then I'm distributing through, and that's how I'm getting this. Is that clear to everyone? And now at this point, you have stuff that vanishes. That vanishes, and all you're left with here at the end is 3 over the square root of 1, which is just 3. All right. Got another one for you. What's the limit as x goes to infinity of x cubed plus x to the 5th? Now, this is not a trick question. What do you think the answer here is?
Infinity. I mean, you plug it in infinity plus infinity, it's just infinity.
This is infinite, right? Okay, so there's no work there. What if I change it to a subtraction?
It'd be negative infinity because the x to the 5th would dominate the x to the x cubed, so it would be.
It would just be infinite.
Yeah.
Yeah, it would be negative because this x to the 5th dominates that x cubed, right? But when we look at it, we're actually getting infinity, take away infinity, and that should be a question mark. Like you have to think this through. Infinity plus infinity, there is no thinking, okay? A big number, huge positive number plus a huge positive number, you're going to get a huge positive number. But when you subtract, well, in that case, things can be different, all right? Now, I want to show you how you can get this answer negative infinity in a slightly different manner. Let's take that problem. Let's realize that there's a GCF in that, a greatest common factor. They both have an x cubed, don't they? So I can factor an x cubed out of each one. And the benefit of doing that is that now I have multiplication. And so I know this becomes infinite. And then be real careful here. What's one take away an infinitely large number squared? So what's
Negative
one
infinity,
minus?
or no, positive, because the x would.
Oh, you're right.
square-
One take away a huge number, right?
Yeah, it would be negative, yeah.
Would be negative. So this is becoming negatively infinite, and you are multiplying the two, right? Not subtracting, because of this multiplication now. And if you have a huge positive number times a huge negative number, you should get a huge negative number. So that's the same problem without using the idea of one of them dominates the other. Do y'all see that I did some factoring?
Mhm.
Okay, now let me show you another problem like that and how we can convince ourselves of the answer using that same property. So what if I say, what's the limit as x goes to infinity of the square root, or sorry, yeah, let's do the square root of x to the third minus the third root of x squared. So that might look weird at first, all right? But let's just think through this. This is infinity cubed square root of that, which should still be infinitely big, minus this, which is infinity squared, but then the cube root of that, which should still be infinitely big. And infinity minus infinity is a question mark, right? That's unknown at this point. So maybe you can make the argument of dominating, right? Like which one dominates the other, but it's not as clear when you have roots involved like this. It's not as clear who wins, right? Or if anyone wins for that matter. So what I'd like for you to consider is this. If this is the first time you've seen this, it's going to look weird. Okay, I'm going to rewrite this. This is x to the 3/2 minus x to the 2/3. So what I'm doing is I am converting these from radicals to rational exponents, which means whatever the power is on x becomes the numerator, and whatever the root is becomes the denominator. That's a college algebra topic. Actually, that's a pre-algebra topic. That's properties of exponents. They'll clear up to that point.
Mhm.
Now I want to do something else, even though I think you might be able to argue with me right now that this one dominates this one, because 3/2 is bigger than 2/3. So I think that would be a sufficient argument, but I want to show you can still do this using this same idea here of factoring. So I want to factor this. And I don't think many of you have ever tried to factor an x out of something like this. So watch what I'm going to do. Again, this is about learning something maybe you haven't seen. What I'm going to do is I'm going to try and rewrite both these fractions to have the same denominators. So do you agree that if you look at 2 and 3, a common factor of 2 and 3 is 6? So I'm going to rewrite these as x to the, let's see, 9/6. How am I getting that? I'm rewriting 3/2. I'm multiplying the top and bottom by 3 so that I get a 6 on the bottom. And then on the other one, I need to do a multiply 2 and 2 on top and bottom. So that should be 4/6. All I did was try to get them to both have the same denominator up here, right? Any questions there? Next step, I'm going to factor out a GCF. Okay, so look at these. They both have this. They both have x, and they both have at least 4/6 in them. See if you agree with that. If I factor x to the 4/6 out, I will have a -1 here at the end. Do y'all agree? -1, because if I distribute that to that -1, I get back this one.
Mhm.
The question is, what's this?
It's going to be x to the 5 to the 6.
Good, 5/6. And that's because when you multiply these, you add the exponents, and 4/6 plus 5/6 is 9/6. And at this point, we're there because this goes to infinity. and that goes to infinity minus 1, which is infinity. And when you multiply two infinities together, you get infinity. Okay. We have an hour left. We are pretty much done with this section, which is 1.6. There's two types of limits. Don't forget, two types of limits in 1.6. You have infinite limits and you have limits at infinity. Two different concepts. So when you're doing your homework, they don't tell you which one to use. So when you're doing them, you're going to have to be able to recognize whether or not it's an infinite limit or a limit at infinity. All right. Before we start the next section, I want to take a moment to talk to you about infinity. All right, because this is, look at this, is just like taking a little mental break. Okay. So when we talk about infinity, right, we use this symbol. Mathematicians sometimes refer to that as lazy 8. Have you ever heard that before? That's pretty funny, right? Math people are pretty funny, I would say. A lazy 8. So the idea of this infinity symbol actually comes from something called a Mobius strip. You may or may not have ever seen this before in your life. If you take a standard little, like a sheet of paper and just cut a strip off of it, a thin strip, then most of us would look at this and say that this strip of paper has two sides to it, right? It has, like, you know, this side here. I'll put something on here so you can see it. So that side, I put some squiggly lines on it, and the other side doesn't, right? So there are the two sides. Let's not talk about the edges and stuff. Let's just say, okay, this is a sheet with two sides. So if I take this sheet with two sides and put my fingers on it, then my index finger is on one side and my thumb is on the other, right? Yes? Okay, now I'm going to take this strip, and all I'm going to do is I'm going to hold one end and not do anything with it. The other end, I'm going to just twist it once. And then I'm going to bring it back over here and I'm going to staple it to the other side. Staple. And you get this thing right here. You'll see that? Okay, now this is it. This is what's called a Mobius strip or a Mobius band. And the unique property of this is that it is now a surface that has one side. There's only one side to the surface. And if you try and debate me that there's still two sides, then I would challenge you to put your fingers on the two sides. You think there's two sides, go ahead and try it. So if you put your fingers there, what you'll notice is that if you follow, you know, your index finger, follow that side and just follow around and keep going, and you will actually wind up at your thumb. And then you keep going around and you will wind up back at your finger. So basically your finger, your thumb and your index finger are on the same side of this sheet. So if you were like a little ant crawling, you know, walking on that sheet, you would just walk forever, infinitely. You would never run into the edge. Does that make sense? That's kind of where this infinity symbol comes from, is this right here. Now, with that said, what most of you don't know at this point in your life is that there are two types of infinity, right? I think everyone has this idea of infinity being like this big thing or this concept of something growing without any sort of bound to it. But in mathematics, there are two types of infinity. There's what's called countable and uncountable. And I think when I talked with you all last, I don't think there's any math majors in here, right? No one here said they were a math major. Okay, so I'm getting, what's that?
I'm doing a math minor.
Okay, yeah, well, so math minors will see some stuff. I don't know how far you'll go, but this is, this idea of countable and uncountable is extremely important in pure mathematics. It's something that you all might see a little bit of, but I want to just kind of try and explain to you what the two are, because it's pretty easy to explain, all right? So think about countably, to say something is countably infinite means that you basically have a set of things that are infinite, but you can somehow count your way through them. A perfect example of this is just the numbers 1, 2, 3, 4, and you just keep going, right? Like you could just start counting right now and you can continue counting until you die, right? And you'll never get to the end of that list. But every single number you say, you are getting through the list, right? You're just going to marching your way through. It's almost like lily pads on a pond. Okay, lily pads, and you're just a frog jumping from one to the next, to the next, to the next. But this pond goes forever, right? And the lily pads go forever. That's what it means to be countably infinite. Uncountable is the idea that the set of things you're trying to look at, there's no methodical way to march through them. So it's like lily pads, but you start at one, and then as soon as you jump to the next one, you realize that you missed lily pads. There's lily pads that you missed. So you say, oh, I missed some, so I can jump back to one. And then you realize when you made that jump, you missed a bunch. And then when you jump to the next one, you realize you missed a bunch. And so there's no systematic way to march through those things. And that's called uncountable. Now, I think that this is the part that I think kind of blows people's minds. Maybe not, maybe just mine. If you just look at the numbers between 0 and 1, okay? Just look at the numbers in there, right? There's your number line, there's a number 0, there's a number 1. Think about all the numbers in there, okay? All the numbers that live in there. Would you agree there's an infinite number of them?
Yes.
Yeah, I mean, let's just think about it, like 1/2's here, right? 1/4's here. Of course, we have 3/4 here too, but we just keep cutting in half. 1/8, 1/16, 1/32. And I could do that forever, couldn't I?
Yeah, you could just 1 over.
I mean, I could
50
just keep
essentially.
cutting it in half forever and ever and ever and ever. And I would never actually get to 0. So do you all agree that the fractions in here are infinite? There's an infinite number of fractions.
Yes.
Okay. Do you think they're countable? Do you think there's a way to count through the fractions like a lily pad, like lily pads?
My instinct is to say yes, but my mind wants to tell me no.
Okay, so the fractions are countable. The fractions are countable, which leads to a question, and this is the part that most people don't know. If you were to take just the numbers between 0 and 1, just look at those numbers alone, okay? If you were to close your eyes and reach into that interval and pick a number off the number line, does it have to be a fraction? In other words, can every number be represented as a fraction? What do y'all think? If I just pick a random number, is there a way to write that number as a fraction? Guaranteed.
Yes.
Put it under or over 1, yeah.
Okay. When I say a fraction, I mean a fraction where the denominator wouldn't be 1, because of course, like 4 over 1, or you can do anything over 1. But I'm saying, as here, when we're looking between 0 and 1, right? When we're looking between 0 and 1.
Yes, because it can be a square root over something, right?
Okay, let me restate it. When I'm saying a fraction, okay, a over b. Okay, when I'm saying if you go in there, close your eyes, pick a number, does it have to be a fraction? I'm saying this fraction has to be where the top is an integer and the bottom is an integer. Integers are like the whole numbers, 1, 2, 3, 4, 5. So like if you pick that number 3/4, right? Then that can be written as a fraction, 3 divided by 4. I'm asking you, is every number between 0 and 1 a fraction? Or are there some numbers in there that aren't fractions? What do you all think?
Fractions.
I'm sorry, Nathan?
Some numbers aren't fractions because of the decimals and everything like that.
right?
Okay, but all right, I agree, but 3/4 is a decimal, it's 0.75, right? We're getting at something here.
So yes, it can.
So maybe yes, it can. All right. So here's the deal. Here's the real deal. I don't want to take too much of our time. When it comes to our numbers, we have basically two types of numbers in our number line. We have what are called rational numbers. Those are fractions. And then we have what are called irrational. And irrational numbers are basically not fractions. Examples of irrational numbers that you've seen in your life that you may not have been aware of are irrational. Pi, square root of 2, e. Remember all those? Like e from college algebra, pi from being a kid, and
I.
then square root of 2, right?
Like I, the
I is
imaginary.
imaginary. That's a
Oh,
little
that's
different.
different. Okay.
Yeah. So irrational numbers, what makes a number irrational is that when you write it down as a decimal, it never stops. The decimal never stops and never repeats. So all irrationals are non-repeating, non-terminating decimals. Any fraction you ever give me, any fraction, I don't care what it is, give me any fraction that's written like a over b. I guarantee that if I write it as a decimal, it's either going to stop or it's going to repeat. So like 3/4, right? 0.75, done. Okay, give me 1/3, 0.333 forever. Repeats, right? Never stops, but repeats. All fractions must either stop or repeat. All non-fractions never stop and never repeat. So the crazy thing is the rationals are countable. The irrationals are not. Which means that if you look just between 0 and 1, just in there, there's a countable number of fractions, but an uncountable number of irrationals. And so here's, when it comes down to it, end of the day, there's one thing I want you to take away from this is this. If any of you have gone and gotten yourself away from the city, right? Just real far out in the country or something, and you've been out there at night and you've looked up into the sky, right? What do you see that you don't normally see in the city?
Stars.
Stars, right? Like any of you have ever seen like the Milky Way, like the legit Milky Way through the sky? It's pretty freaking awesome. It's almost overwhelming because nowadays, most people have never seen the Milky Way, like other than like in a book or on a video or on, you know, like not in person. It's pretty crazy. But okay, so imagine you get away from the city, you're looking up in the sky and you see all these stars, right? The stars are the fractions. They're everywhere. Like it's, you can start counting them, but they're kind of like, you'll never finish, right? You'll never really finish counting the stars, but there they are. They're 1, 2, 3, 4, 5, right? The stuff that's not fraction, I mean, the stuff that aren't fractions is the black. Okay, the darkness is the irrational numbers. It's like, it's everywhere, but nowhere. You know what I'm saying? It's like you can't point one out. You can't point to one of them, but it's like there's more of it than there are the stars. That makes sense? That's the way our number line looks. If you were to look at our number line, scattered within that number line are a bunch of stars, which are fractions. But there's a bunch of black too. There's a huge amount of black in here. And so if you try, you can jump lily pad over stars. You can jump across the stars, but you can't jump across the black. Because as soon as you make a jump, you've missed an entire chunk of black. I hope that makes sense.
It's actually a really good explanation, at least for me.
Okay, good. So infinity, there's two types, countable and uncountable. I'll tell you one more thing. This is one of my favorite stories. I'll make it real short. When I was in grad school, I used to go out once a month because when you're in grad school, you have to commit your life. Okay, so all I did was math. But once a month I'd go out to a club and I would just like let it go, you know, just like get crazy at a club. And I would take a taxi. They didn't have Uber when I was in grad school. So I'd take like a cab and I just get ridiculous there, right? So being out and socially, you know, you'd meet people and stuff. So I used to have this like minimum, if I met a girl, I'd be like, there would be like a minimum question that she would have to be able to answer, a math question, for me to even have an interest. And it wasn't because I was arrogant, it was because it's like all I did was math. So if we have to have some common interest, right? So the question that I would ask her, I actually can't, you wouldn't be able to answer it yet because we haven't even talked about it, but I'd ask her what the derivative of X is, okay? It's a Cal 1 question. Should be a very simple answer. So there, one night I met this girl and you know, we were dancing, and then finally I went to the bar, she came up to me and we were talking, and I asked her, what's the derivative of X? And she was like, she got it right. And then I asked her one more question. I said, if you take, this is literally the question I asked her. I said, if you take the interval 0, 1, what's the probability of picking a rational number out of that interval? Okay, so basically what I'm asking her is, if you were to blindly reach into this interval 0, 1 and pick out a number, what's the probability that it's a fraction? Right? That's what I was asking her. And the answer, the correct answer is 0. There is absolutely no chance that if you randomly reach into 0, 1 and pick a number, there is 0 chance you will get a fraction. Why? Because the fractions are countable and the darkness is uncountable. So you are guaranteed to get the darkness. It's a crazy idea, but all of our measure theory is based on it. So she answered that. I was like, my mind was blown, you know? So unfortunately she didn't live here, and that's the only time I ever saw her like face to face. And I still talk to her. She's a friend of mine, and she programs robots that build cars. So like when companies want to go like set up a what do you call it, assembly line, and they want to set up all the robots to come down and do the welding and manufacturing and stuff, she goes in there and sets it all up, gets the software all going, and that's what she does for a living. Pretty crazy. So I kind of like unintentionally asked this crazy question to her, and she knew it. I was like, it's just, that's not common knowledge, right? That's definitely not common knowledge. So, all right, so I went off a little bit on a tangent there, but I just want to take a little break from the calculus for a minute. Are y'all ready to get into continuity?
Yes, sir.
Okay. All right, here we go.
I feel bad. You always ask, and I feel like I'm answering for the class. So I feel like there's some animosity.
You're going to be the
amongst people.
spokesperson. Cody is the spokesperson for the class. So if Cody's ready, we're all ready. Okay, unless somebody else speaks up. Well, it doesn't matter, Cody. Even if you say you're not ready, I'm still going.
Okay, fair enough.
I'm just asking to be nice.
The illusion of choice.
Exactly, the illusion of choice. That's right. I was at a high school graduation last night, and they had all the students sitting out in the Alamo Dome 6 feet apart, right? And they, before they sat down, they were all standing in line for like 30 minutes, like right next to one another. I'm just like,
Hurry up and wait.
you know, like
That reminds me of
the illusion of safety, right? All right. Continuity. All right. So this is a new concept. This is a very easy concept to understand visually. It's a little harder to understand algebraically. So let's start with the visual idea of continuity. So I want you to look at this function. And the question of continuity comes down to this. Can you draw it without picking up your pencil?
No.
That's basically what continuity is saying. So if I asked you to draw that graph, could you do it without picking up your pencil?
No.
No.
Right? You've got a hole. Do you all see the hole? Right? We've got a hole. Now, that doesn't fly in terms of math, okay? We have to have a more precise idea of continuity. I can't be like, can you draw without picking up your pencil? It's got to be a little more rigid than that. So let's look at what's happening here. If we take a look at this X value, which happens to be 2, let me ask, is it Jair, or how do you say that?
Jair.
Jair. Okay. change it here so I can, it's Jair. I think I said that right the first time, didn't I?
Yeah.
Okay, Jair. Okay, Jair, I'm going to ask you some questions. I'm putting you on the spot. You ready?
Okay.
Okay. Does the limit as x approaches 2 of this function exist from the left-hand side?
Yes.
Okay. Can you tell from the picture what it is?
8.
8. Okay, so good. Jair is saying, what I asked Jair is, if you were to come in here from the left-hand side and approach 2, is the function approaching a y value? And he said, yes, 8. You all agree with that?
Yes.
Okay, Jair, how about from the right?
It does also exist, and it approaches 8 as well.
Okay, so what we have here is that the limit as x approaches 2 from the left of this function is 8. We also have that the limit as x approaches 2 from the right is also 8. But Jair, what about the function's value at 2? Can you tell me what's happening at 2?
It's undefined.
Undefined. Now, Jair, if the function was defined at 2 to be 8, then wouldn't that fill that hole in?
Yes.
And if that hole was filled in, then could you draw it without picking up your pencil?
Yes.
Yes. So this function right here is not continuous at 2 because not because the limit from the left doesn't exist or from the right doesn't exist. It's the fact that we have the hole that causes us to have to pick our pencil up, right? So this idea of continuity is that we need 3 conditions to be met simultaneously. We need first the limit from the left to exist. We need the limit from the right to exist. For those two to be the same, and we need this to exist and to be the same value. If all 3 of those things are true, then you can maybe imagine that you wouldn't have to pick up your pencil. Let's look at another one, and hopefully this will start to become more clear. I've got to scroll down, which means I have to erase that. Okay, Matthew? Are you there?
Yes, sir.
How's
Yes.
it going? Okay, look at this, Matthew. I want you to focus your attention at 2.
Mhm.
Okay. Does the limit from the left exist?
Yes.
Okay, what is it?
It approaches 8.
8. Okay, from the right?
It approaches 8 as well.
8. Okay, is the function defined at 2?
No.
Do we have a dot? Like at 2, do we have a place?
Okay.
So we do,
yes,
right?
at 6.
Right there, we do have a dot. So the function is defined, but what is it defined to be? It looks like
6.
It's 6, right? So because it's 6 and not 8, God, it would be nice if it were 8, right? If it were 8, then I'd be able to draw this without picking up my pencil. But because it's 6, I've got to draw it up, pick up my pencil, put that dot, go back here and continue, right? So this is not going to be continuous either. You'll see that?
Yes.
Yes.
Okay. This one is, right? Because as we approach 2 from the left, it's headed to 8. As we approach 2 from the right, it's headed to 8. And at 2, it's also 8. And therefore, we have continuity. Let me see, hold on. Okay, yeah. I'm gonna get you to the definition in a minute. I just want you to look at this visually first. Look at this one. So Caitlin's up. Caitlin, how's it going?
Good.
Okay, Caitlin, does the limit as x approaches 2 of this function exist?
From the left or right?
From the left.
Yes.
Yes. And it looks like it's about what?
8.
8. Okay. How about from the right? Does it exist? Does a limit exist?
Yes.
Okay. And what does it appear to be? Kind of hard to see.
I guess 4.5 or 5.
Yeah, 4.5 or 5, right? Something like that. So the limit from the left is going to 8. The limit from the right is going to 5. And then what about at 2, Caitlin? At 2 is the function define.
No. Well,
You
one
see
of
the
them
dot?
is.
You see the dot up here?
Yeah. So
Okay,
one
so
is
that means at 2, it looks like the function is defined to be 8.
8.
So Caitlin, to make this be able to draw it without picking up our pencil, because we do, right? We would have to pick up our pencil here. The only way to fix that would be to take this entire piece and somehow, like, instead of making it go down here, we would need to make it go into here, right? Like that. And then it would work. Like then I could draw it without picking up my pencil. Yeah. So what's wrong with this one? The reason that we are not continuous here is only because the limit from the right doesn't match up with the left-hand limit and where the function is defined. Let me give you the definition. Let me go up and give you the definition. Okay, here it is. Definition of continuity at a point. A function f is said to be continuous at some value x equals a if the limit of the function is equal to the function's value at that point. That's it. That's the simple definition of continuity, but there's a whole lot right here. Okay, there's a lot of information in just this simple equation. So when we look at that, this right here means that when we're approaching a, that when we come in from one side, it must be equal to what's coming in from the right side. And that's because there's no plus or minus on the a. So for that limit to exist, from both sides has to be going to the same place. Do you all agree with that? Do you all understand that's what it means for the limit? But not only does that have to be true, we also need that it's equal to the function's value at a, which means that I need that to be filled in with a dot like that. And that will guarantee us continuity at that point. The dot's there and both sides are going into that dot. If we have that, then you have continuity at that point.
So basically the function of x has to equal the function of a, or okay, never mind.
Yeah, the limit of the
Yeah.
limit as you approach a of the function has to be equal to the function's value at a. If any of those are, if the limit doesn't exist, then it's done. It's not continuous. If the function's not defined there, it's not continuous. You're going to have to see a couple of examples of this for you to understand, I think. Okay, so let's see. So the basic idea, right? The basic idea is that for a function to be continuous, we have to be able to draw it without picking up our pencil, right? That's basically what it means to be continuous. If a function is not continuous at some point, then we say it is discontinuous at a. That's just definition. There are three basic types of discontinuity. So there are three different scenarios that you can run into where a function would fail to be continuous. The first one is what's called a jump discontinuity, which you can see right here. If your graph ever has a break or a jump in it, then you cannot possibly be continuous. If you have what's called an infinite discontinuity, so if you have a vertical asymptote, it's impossible to be continuous because you would have to pick up your pencil. Because you have vertical asymptote, you'd have to pick up your pencil and then draw the other side. And then the last one is what's called a removable discontinuity, where everything is almost right, except that you've got a hole in it. And so again, you'd have to pick up your pencil. All right, so I'm now going to talk about a slightly adapted version of the definition. It's called continuity from the left and continuity from the right. So look at this function right here. And I want you to think about the idea that if you were to draw this, you would not pick up your pencil, not pick up your pencil, not pick up your pencil, and then you would be defined. You have a dot here, right? So everything from the left is good, isn't it? Like you can draw it without picking up your pencil, and at 2, you've got your dot there. This would be an example of what's called left continuity. You are continuous from the left. but from the right, you're not. And it's because that dot is not down here. If I simply move that dot down here and get rid of it up here, now this would be right continuous and not left continuous. Which is this scenario here. So it's like left and right continuous is like almost continuous, but one of the sides is messed up, right? Now, continuity on an interval. So if we have a function that is only defined between 2 points, like an interval, then all we have to look at is that you can draw it without picking up your pencil in between those 2 points, right? So as long as we can do that, then we would say it's continuous on the entire interval. You do not need to worry about what's happening here and here because the interval is closed. So you don't have to worry about what's happening to the left of 1 or to the right of 3 in this case. Now, all of this is great, these definitions and these basic ideas. Really, at the end of the day, it comes down to one thing, and that is what functions that you've studied in your life are continuous. And this theorem tells you which ones are. So everything you studied in college algebra, all polynomial functions, go back to lines, parabolas, cubic, fourth degree. When you drew those, right, and you graph them, you never have to pick up your pencil to graph a polynomial function, right? Here's an example of a polynomial function. Draw it without picking up your pencil. Rational functions are continuous, but only on their implied domain. So let me show you a picture of a rational function. Here's a rational function. Rational functions have vertical asymptotes. So anywhere the function is defined, which would mean in these blue areas, anytime you can draw, it's continuous. You do have to pick up your pencil and go over the asymptote, but that's not in the domain. So as long as you're in the domain, you're guaranteed to be able to draw it without picking up your pencil. All trig functions, same thing. You should be able to draw it without picking up your pencil as long as the values are within the domain. Exponential functions, right? You can draw it without picking up your pencil. Logarithmic functions, draw it without picking up your pencil. Those are all well-behaved functions. Oops. Another property is that if you take two continuous functions and compose them together, that means put one inside of the other one, you should still have a continuous function. So I've given you some examples here. I'm going to make this a little bigger so you can see this. Oh, that's a lot bigger. Maybe too big. There we go. So this, what you're looking at right here is the graph of sine of x squared minus x. So x squared minus x by itself, that's a polynomial, which should be continuous everywhere. And then you're plugging it into a trig function, sine, which is continuous everywhere. So when you put the two together in composition, your answer, your graph, should be something you can draw without picking up your pencil. That's what this theorem is saying. Composition of continuous functions is continuous. Let's look at another one. E to the cosine of x. There's the graph of e to the cosine of x. Again, cosine of x is continuous. The exponential function is continuous. You compose the two, you get continuous function. That's another one. Here's another one. Here's another one. Okay, so that's all that theorem is saying. Put two continuous functions together, it's still continuous. And this leads us to a very important theorem. This is actually one of the most important theorems in math, especially for computer science people. It's called the intermediate value theorem. So the intermediate value theorem says this. Suppose f is a continuous function on a closed interval. Okay, so what does that mean? We have a function on a closed interval, meaning between two values of x, a and b, and it's continuous, which means we can draw it without picking up our pencil. And let's say that the two endpoints are not the same. So what happens at A is not what happens at B. So here's an example of that right here. Okay, so notice that if I say this is A, I start here. That's f of A, that's how far down it is. And then here's B. So that distance from here to here is f of B. Notice that this function between them is continuous, right? I can draw it without picking up my pencil. And the left endpoint f of A is not equal to the f of B. Okay, so that's what we have to assume for this theorem. Okay, we have a continuous function, closed interval, and the two endpoints are different. Then what the intermediate value theorem says is this. If you let n be any number in between f of A and f of B, there exists a C in the interval AB such that f of C is equal to n. What? Okay, what the hell? Okay, this is confusing, right? Let's see. I'm going to try and illustrate this. Here's our continuous function. We restrict it to a closed interval. There we go. Right, so we're restricted to a closed interval. These two endpoints are not the same, right? The theorem says if we choose any n between those two outputs, okay, so you pick any n you want that's between 13 and negative 12. So somebody tell me when to stop.
Stop.
Okay, right there. Oh, n is 1. Okay, what are the odds of that happening? Okay, so someone picked a value between the two outputs, negative 12 and 13. What the intermediate value theorem says is this: guaranteed, there must be some value on the function. There must be some value between the two endpoints that when you plug that into the function, you get 1. I'm going to need to move it because it's hard to see it there. I'll move it to, let's move it to 4.8. So if someone says 4.8, what I can say is that there has to be some value that I can plug into the function that will spit out 4.8. Guaranteed. Guaranteed. Has to be there. And you can do that for any value. Does that seem trivial, like almost trivially stupid, this idea? Or does it seem?
I mean, in a sense, it seems like common sense to it if you think about it. But just like if it's on a line that's continuous and it's an interval, somewhere on there is going to be a point that matches what it's covering.
As long as the graph is continuous, though, right? Like if that graph has a break in it, it can have a problem. Look at this. Like, look, if I take this and I try and restrict it between here and here, this is not a continuous function, right? So I make sure that the two endpoints are not equal. So this spits out 13, this spits out negative 12. But now when someone picks, if they happen to pick a value right there, there's no part of my graph ever achieves that. So I need the continuity for this theorem to be right. Now, the name of the theorem, intermediate value, it comes from the idea that if you take any value between negative 12 and 13, any intermediate value, you are guaranteed the existence of some number that would plug into the function and spit that out. Now, I said this is important for math people. I mean, not math people, computer science people. Here's why it's important. Here's why this is so important. I'll show you. I'm going to go to Wolfram Alpha. I know that there are other websites out there. I'm going to ask this to solve the equation cosine of x equals x. And I'm going to get the answer. We'll come back to it in a moment. But what I just asked Wolfram Alpha to do is solve this equation. Cosine of x equals x. Okay, now I'm going to ask you to solve it. And if I ask you to solve that for x, you should look at that right now and you should be like, I have no freaking idea. Because there is no way to do it. There's no way to solve that. You might be like, okay, well, you know, what I'll do is I'll be clever. I'll bring in cosine inverse on both sides. And if I bring in cosine inverse, then I know that I can kill off the cosine and spit out the x on the left-hand side, which is fabulous. But what have you done on the right-hand side? You've taken cosine inverse of x. So now you've got x equals cosine inverse of x. Okay, that doesn't tell me what x to, this doesn't solve the equation. All this does is rewrites it in a different way. There's no algebra out there. There's no technique you've ever learned. There's no technique you're ever going to learn that's going to be able to solve that. All right. So we go to a computer and a computer can solve it. Right. Wolfram Alpha just did it. 0.739085. Okay, that's what happened. Or that's what it's saying. And let me make this a little bigger. Notice that it says x is approximately equal to this. That means that it's, it stopped at some point. It rounded a little bit. It stopped. But if I wanted more precision, I could have it give me more digits, and it just rounded more. It just went out and made it more precise. And if I want more, I can get more. If I want more, I can get more. I don't know how much more I can get. Holy shit. Is it going to make me buy the pro version at some point? Oh, I think I finally brought it to its knees. Okay, I guess I'll have to come back to this. So look, this computer has solved this equation with accuracy out this many digits. That's crazy accuracy right there, right? So what is the computer doing? How is the computer solving this? Believe it or not, it's the intermediate value theorem. That's all it is. So watch how this works. If you take this equation and move everything to the left-hand side, if you're computer science, then you should pay attention to this, all right? This right here, I'm going to rename that f of x. I'm going to call that a function. Just going to call that a function. Now, remember, in college algebra, pre-cal, all the math classes you've taken before this, if you were ever asked to find the x-intercepts of a function, what do you do?
Look for zero. You look for the zeros.
You set it equal to
zeros
0,
first.
right? So if you ever want the x-intercepts of a function, you set the function equal to 0 and you solve, right? So do you all agree that if I write it this way and call this left side f of x, then what I really want are the x-intercepts of the function f of x equals cosine of x minus x. That's what I really want then. To solve that equation is equivalent to me asking you for the x-intercepts of this. Yeah? Okay. So, my x-intercepts. Let's say here's kind of an approach I can use. I'm going to make a guess as to the answer. I'm going to make a complete guess out of the blue right now as to what I think I can plug into this that will spit out the answer 0. So here's my first guess. I'm going to let x be 0. Okay, let x be 0, and I'm going to guess. Let's see what happens when x is 0. If I plug 0 into the function, I get cosine of 0 minus 0. Cosine of 0 is 1. 1 minus 0. Okay, I get 1, don't I? I get 1.
Yep.
Okay. I'm going to make another guess. That guess wasn't right. I'm going to make another guess. X is 1. Okay, if I plug 1 into this function, then I'm going to do cosine of 1 minus 1. That I'm going to need my calculator for. Cosine of 1. I'm in radian mode, not in degree mode. Radian mode on my calculator. And I get negative 0.000152. Oh, wait, shit, I'm in degree mode. I just told you to be in radian mode, and I'm in degree mode. I don't remember when I switched it to degree. Okay, I get negative 0.456. So I made a guess of 0, and it spits out 1. And I made a guess of 1 and it spit out this. So I'm really hoping it'll spit out 0, right? So do I keep guessing or?
You go in between the two.
Something, yeah. So something very important just happened with these two answers. One of them is positive and the other one is negative, right? So that means that if I think about this graphically,
We cross the y-axis.
I have to cross the x-axis at some point. At 1,
Or yeah,
or sorry,
sorry.
at 0, we got 1, didn't we? So I know that if I graph this, I'm up here at 1. And I know when I plug in 1, I'm down here at negative 0.45. So I don't know, like here's negative 0.5. So I'm somewhere around here. That's where I am, right? And I'm looking for the x-intercept. The only way you can go from a positive number to a negative number is if you somewhere in between cross the x-axis. Why do I know that? Because it's a continuous function. And so it has to be drawn without picking up my pencil. Why do I know it's continuous? Because that's continuous and that's continuous. Polynomial and a trig function. So that means they cross through somewhere. Now, I don't know where. It could be here, could be here, could be here, right? So what I would do now is I would check another point in between. So why don't we take the most natural point, which would be 1/2. And let's plug that in. So I do that on my calculator. I'm just going to tell you what the answer is. I get 0.3775, which means that at 1/2, I'm at 0.3. I'm still positive, right? Still positive here, which means that it has to be between here and here, to the right side of 1/2, not to the left, right? So what should I do now?
A little smaller.
Okay, so I should check another point, shouldn't I?
Mm-hmm.
Probably halfway between those two, like 3/4.
Right.
So I'm going to let x be 3/4 and plug into the function. Here we go. And I get a negative number. I get negative 0.0183. Ah, okay, so that means now I'm below, which means now I know the answer is between 1/2 and 3/4. Does that make sense? I'm between here. So now why don't we do this? Let's go halfway between there and do it again. Now this could become tedious, couldn't it? Like trying all these, right? Over and over trying them. Not for a computer though, because what can a computer do? A computer is can very easily and extremely fast, right? Can do arithmetic. So if I could just program a computer to do this, like write a code for this, to run this algorithm, where what it's doing is it's picking 2 arbitrary test points, checking to see, so I have to run a test to see if I get a positive and negative. If I do, I have it bisect that interval, check again. If I get a change in sign, I bisect again. And then I just keep doing that. And what happens is you start with the full interval, and then the first iteration, you cut it in half. And then in the second iteration, you're going to cut that in half. And then in the third iteration, you're going to cut that in half. And what happens to the window? It starts to come together, doesn't it?
Mm-hmm.
And the computer will never find the answer, okay? It's never going to find it. All it's going to find is a window. But the thing is, you can do this millions of times in a snap, right? So you get down to a point where the window is so freaking small that all you do is just say, take the middle of that window, there's your answer. And it's somewhere in that window, but it's such a small window, it's precise enough for anything you ever need to do. Right? We're talking about like I showed you here, fewer digits. So when I was doing this in the beginning, it ran an algorithm and it said, okay, my window came down, it got really small. How small? Like that window, the difference between the 2 points it was testing, that distance between them was like smaller than 0.0000, how many decimals? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So like, that's how small that window was. That's how narrow that was. And then I said, okay, well, look, I'm not happy with that. I need more precision. I hit more digits. and it just did more of the algorithm and made it even smaller. It just tested like hundreds of thousands of points. Does that make sense?
Right, so then if it can't ever
Simple.
find it,
Won't
what's
ever
happening
find
when you run out of digits? Is it just the end of the algorithm that it can run, or its capabilities, or what?
Oh, you'll never run out. You'll never, because look, if you have 2 points, you can always keep on making that smaller. You're never gonna
Right.
run out of numbers, right?
Right, I'm asking why, if you can't run out, why does the computer eventually stop generating, like with Wolfram Alpha here, it eventually stops
okay.
giving you more?
It's a built-in it's a tolerance that's built into the program. So
Okay.
it keeps running the algorithm. Every single time it runs through the loop of the algorithm, at the end, it measures the distance between the 2 points it tested. And it says, if that distance is bigger than this number, continue to do the loop. And as soon as it tests to see that those 2 endpoints are now smaller than some predetermined number, it stops. Does that make sense? Your calculators work the same way. There's a thing called float on your calculators where you can tell it how many decimals you want it to stop at. And that's basically just going into the brains of the computer calculator and saying, okay, from now on, anytime you do a number computation, like stop at a certain point. Does that make sense, Cody? Just gives you an exit point for the routine.
Right, yeah, I imagine they also program it in, because if you didn't, the computer or calculator would just
It just
probably
get
die.
stuck in a loop. You just get stuck in a loop, and then
Yeah.
there'd be some limitation. You'd run out of memory, right? You'd probably run out of memory before you run anything else. But so, I mean, in terms of like what this computer program did, there's nothing magical. It's basically addition, subtraction, multiplication, division, and a bunch of logical tests that were run in some very simple code. For computer science people, it's pretty simple code to code that up. It's actually called the bisection method. Does it make sense? Keep bisecting, bisecting, bisecting. And then, computer scientists learn later that there's more efficient ways to do the problem. Like there's other algorithms you can write that will get you to that same answer much faster. There's different things, and then you learn them, and you learn how to code them, and you learn their strengths and weaknesses and things like that. But all of it depends on the intermediate value theorem. You have to have that. You have to know that if you go from positive to negative, you're guaranteed to go through 0. And the only way we can guarantee that is if we have a continuous function. If it's not continuous, we don't have it. Okay, 4:22, we've got 8 minutes. Oh yeah, here it is right here. So here's a picture of it. Okay, this is the actual graph. And so we plugged in 0, got a positive, plugged in 1, got a negative, and that means somewhere in between is the real answer. All right, I think I'm going to skip this problem. There's no way I can do this in the time we have left. And that means I need to make a change to the homework assignment. So on 1.5, we're going to skip something on the homework. And don't worry, it's not going to be one of those things where it's like, man, we didn't cover that in my Cal 1 class. Don't worry, it's such a subtle thing. You don't need to worry about it. 1.5. Number 34. Number 34. Don't do 34.
We did 11 through 28 on the last one. But
yeah, and all I wanted you to do there is 11 through 28. But now what you can also do on that one, on 1.4, 49 through 56. So make sure you do this. So
you said 49 through what?
Yeah, 49 through 56. So 49 through 55. 65 we won't do right now. Okay, so that's it. The problems you should have done now, or by next time we meet, is everything highlighted in yellow. In 1.6, this is the same assignment, so it's the exact same thing. It's out of the same section. So everything in yellow there is what you should be working on for when we meet again.
You want the 1.5, the 2, 3, 4, 5, 11, 15, 16.
Oh, I missed that one, yes, sorry. Yeah, let me see. Let me see. Yeah, see how you do with it. Okay. So this is going to complete chapter 1. We've got the basic idea of the limit in place. And now what we do is we venture into chapter 2 is we see how we're going to use this idea of the limit to get to the, I'll bring this back up, to get to the first question that we asked to start this whole class. And that is, if somebody gives us a function, is there a way to find the equation of a line that would be tangent to that function at a certain point? Somehow the limit's going to allow us to do that. So chapter 2 is going to be important next week. And then we have a test. Let's see when our test. Our test isn't next week, right? It's the week after. Yeah, so our test is 2 weeks from today. And we have a ton of work that's crammed in there. All right, everyone. I don't think I have anything else. Thanks for your attention today, and thank you for having your cameras on. I've basically made a screenshot over time today. I've taken a few of them just to see who's here, so that way you get credit. I'll hang out for a few minutes if anyone has any questions. Other than that, have a great weekend.
Thank you, sir.